everyone. I welcome you all to the live session on Computer Vision by Intellipaat. This session is conducted by multiple experts who will be teaching you everything about computer vision from basics to advanced level. Before we begin the session, make sure to hit the subscribe button and also like our videos so that it will motivate us to come up with more such interesting live sessions in future as well. On saying that, let's see the agenda of the day. Firstly, we will begin with Introduction to Computer Vision. In that, we will tell you what is computer vision and why do we need it. After that, we will learn about use cases of computer vision. Then later on, we will see the applications of computer vision. Post that, we will learn about image resizing and cropping. Post that, we will learn about Keras and Keras augmentation model. Then later on, we will learn about implementation convolution with augmentation. Then finally, we have covered imagenet. So, this is the agenda of the video. This session is going to be very interesting. So, stay tuned and watch the video till the end. Now, let's begin the session.
So, what is computer vision? The question is quite natural to appear in our mind, and we have to understand what computer vision actually entails. Let's take a look at that. Computer vision is a field of computer science that deals with gaining understanding about the contents of a visual data. This visual data includes things such as images, videos, GIFs, and many more. The reason why it's called computer vision is because before computer vision, we had access to images. Our computers can understand and process the image, but the processing essentially just meant converting some data into other formats. So for instance, if we had a colored image, we can convert it to a black and white image. The computer had no idea about the contents of the image, whether it contains the face of a person you know, a famous personality, whether it is the image of a tree, a mountain, some kind of an animal, so on and so forth. So that was not very useful, mainly because this allowed us to manipulate the data that lies beneath the images, but it does not allow us to provide any contextual information about the images. So for instance, if I wanted to search for an image out of the images that I have on my phone, give me an image where there is a photo of me inside it. It could be a selfie, it could be any kind of image, but I should be present inside that image. Before computer vision, our computers, our applications were just not able to do that because they had no idea what an image contains. The part of the problem was that image data is very complicated. It may look simple on the outside, but because images are made up of several colors, several variations of colors, gradients, and they can be manipulated in several ways, it can be really difficult to understand well what computer vision actually is. So in cases like this, when we're trying to understand what computer vision is, an important idea to understand is that our brains are much better and much more capable of understanding visual data. We do it all the time. We take a look at a mobile phone, we understand what the phone is, we can understand contextual information about the phone, that is how large the screen is, what's the weight, how does it look, what color of the mobile phone is there, what company, brand, so on and so forth. But computers were not able to do so. With the advent of machine learning and data science, now this is very much possible. Now we can teach computers what a mobile phone looks like, and then when the mobile phone is seen in any of the images or videos, we can very easily understand what it actually means. Now that is a very narrow understanding of what computer vision is, because in computer vision you might want to not just be able to do it with a mobile phone, but there are several fields, such as if you are trying to analyze the video of a traffic, you might want to know which of the images or which of the people in the traffic or vehicles in the traffic are moving at a pace that is not suitable for them, and so on and so forth. So that's what computer vision is. Basically, it allows computers to understand visual data, such as data contained inside an image, a video, so on and so forth. Let's take a look at why computer vision is useful. We have understood what computer vision is and what it is useful for, but let's understand why is it useful. What benefits are there? Computer vision is useful for several reasons. Let's understand these reasons. I've mentioned only a few, but let's understand them one by one. First one is contextual understanding. This is by far the greatest achievement of computer vision, which is contextual understanding of images and visual data. Give you an example. If an image contains a person that is inside a vehicle, that is in an image that a computer vision can understand, and depending on how the computer vision algorithm is set up, it could even understand whether the person is driving or is just a passenger. That's the contextual understanding that we're talking about. Before this, all we had to do, we had to process the image on our own, and then we could label it on our own, but there was no way of it being understood by the computers automatically. Computers had no idea because they could not see the images, they had no vision per se. So that's why computer vision was helpful in providing contextual understanding. Another good information would be another good use case for this would be, or good benefit of this would be, that since contextual understanding is built using computer vision, we can even use it in different areas such as security, where one person might be allowed to do some things but not the other things, and so on and so forth. So that's what we mean by contextual understanding. Then comes accurate predictions. Before computer vision, predicting data in visual data was very tiresome, very cumbersome, and was not very accurate as well. We got around the accuracy of 60%, but that was not really desirable. So to get over that hurdle, computer vision makes processing videos, live streaming data, images, GIFs, so on and so forth, and segregating them, classifying them, or making some prediction based on that data very easy. And understanding the images as well becomes very easy and very accurate. So accurate that it's now feasible to be used in the real world applications, which we'll see in a few minutes. There's reduced costs. Computer vision has significantly reduced the cost of understanding the images and its contexts. That has mainly happened because computer vision applications are now viable. We can deploy these applications on several platforms, be it a low-powered mobile phone, be it a high-powered mainframe. Computer vision applications can run on several applications or several platforms. So the cost that we sort of invest in creating a computer vision system gets paid over time because of the wide variety of platforms and the wide number of users that it can be accessed by. Then comes user experience. There are several things that a computer vision system you can do to enhance user experiences. For instance, a very useful use case of computer vision is you have an image or you have some product in front of you that you want to get some information about. Now, before this, what you would have to do is you would have to use a textual interface in which you would have to type in the text depending on the image that you have. Now, on the other hand, what you could do is now use your camera to point at the product that you want to buy, and the computer vision system will take it over from there and will give you all the information that it can find on the internet based on the product that it has. That's the real advantage of using computer vision. It enhances the user experience to a level that was not possible before computer vision was a thing. So computer vision can be really useful for other aspects as well, but these are the four major advantages of using computer vision. Now let's take a look at some of the use cases of computer vision. These use cases are just a mere list of things that can tell you what are the kinds of things where you can use computer vision. Obviously, you can use computer vision for other things as well, more things than I have mentioned here, but let's take a look at the things that we have mentioned. So there are several use cases for computer vision. First one is image classification. Image classification is by far the most primitive way or the most primitive use case of computer vision. The first thing that comes to mind when we're talking about computer vision is this primitive understanding, which is where you get an image and you try to basically, after getting the understanding of what it actually is, what you do is you classify that image, provide a label on it. So for instance, it could be a label based on some binary classification, whether the image contains something or not, or it could be a more broader aspect of classification in which we are trying to label the image with all the things that it contains. For instance, if it's an image of a person driving on a mountain, then the labels could be person, car, road, mountains, driving, vacation, so on and so forth. All of this is now useful and feasible using computer vision. Then comes security systems. Computer visions play a major role in security systems, as you can, for instance, put in the faces of the employees that you want to have access to a particular resource, and then when the computer vision system activates, any person that is not inside the database of the persons who should have access to the images or to the resources is not going to gain access because computer vision is able to classify the person as being authorized or not. Computer vision systems also allow you to basically just log the information about who came in and who went out, so the security systems can be really sophisticated as well. Video segmentation is also a really huge use case for computer vision. Since we are able to derive contextual understanding of images, we can segment videos into several portions. We can pick out portions, we can pick out people that are present inside the video, and we can separate the videos based on what data it contains. Google uses video segmentation using computer vision quite a lot, so you can take a look at that as well. And then there's live streaming. Computer vision systems are also now capable of processing live streaming data. So, for instance, if you have um, certain certain use cases in which you don't want certain images, copyrighted contacts, anything to be shown on the screen, even when you're live streaming, and you don't want to do it even by mistake, there are computer vision systems that can allow you to do so. So basically, your data, instead of going directly from your computer to the streaming service, and from the streaming service to the person who should get the data, what happens is the streaming service firstly processes the data, maybe it offloads it to some other computer vision system, and that will analyze each frame of the video, see if there is anything that is worth clipping out or pixelating, and that will be done automatically. It does take a lot of processing power to do so. So this could be a little costly, but that really is a use case, a valid use case for computer vision. Now, let's take a look at some applications that use computer vision. These applications are applications that are very famous and use computer vision quite often and quite a lot. So let's take a look at these one by one and understand where they use them. You may be familiar with some of those, so let's dive in. There are several applications nowadays that use the computer vision system. Some of these are Snapchat, Amazon Go, Pinterest Lens, and Google Lens. Let's take a look at them one by one. So for Snapchat, if you have ever seen the filters that are provided by Snapchat, and now is a feature that is available in several applications such as Facebook and Instagram as well. Well, these features are implemented using computer vision. All you might consider it to be an augmented reality feature. Well, that does come under computer vision. So if you are trying to understand augmented reality, where you are able to put some things inside a video that they are not there, then Snapchat is a good example. Filters are a good example of that, and computer vision is useful in that regard. Then comes Amazon Go. Amazon Go is a Amazon store in which you can walk in, buy something, and just leave, and the amount of the products that you have bought will be deducted from your payment systems. This is a convenience store. It is very popular. It's not a lot of branches are available there, but it makes heavy use of computer vision systems, along with other systems such as cryptographically secured sensors and many other kinds of things. But at the end of the day, it makes the shopping experience much easier, and Amazon Go is uh, a very heavy user of computer vision systems. Then comes Pinterest Lens. Pinterest Lens is actually a very important tool if you use Pinterest, in which basically you can point it to any of the things that you want to be searched on Pinterest. So, for instance, if I want to take a look at a recipe of a dish, what I can do is point it towards the dish. The Pinterest Lens will find all the images that look similar, and then you can choose one and look at the recipe of that image. Similarly, there are many other things that Pinterest Lens could do, and that's why it's so useful, and it makes heavy use of computer vision as well. Finally, there's Google Lens. Google Lens allows us to basically perform a whole variety of tasks ranging from scanning barcode, identifying products, identifying images, identifying things inside images, people inside images, make Google search, image search, all of that. And that is one of the most popular use cases for computer vision. This application is by far the most popular one among the bunch that we are discussing that uses that uses computer vision heavily.
So there are a lot of deep learning frameworks available today. So now my question to you guys would be, why should we use Keras out of all of these deep learning libraries? Well, let's understand. So the number one reason to use Keras would be it prioritizes developer experience. So Keras is a framework which is developed for humans and not machines. That is, it is very easy to code with Keras. You just have to keep on adding layers which you can invoke with functions, and you can keep on building neural networks. So it is that easy to work with Keras. And then Keras is also broadly adopted in the industry and also among the research community. So all of the PhD scientists over there and all of the data scientists, their most widely preferred deep learning framework is Keras. And the next reason would be it is very easy to turn all of these Keras models into end-to-end products. So let's say if you develop a simple prototype with Keras and if you want to launch it on some platform, then you can easily do it. So you build a model and then you can easily launch it on, let's say, Android, iOS or any other operating system as an end-to-end product. And Keras also supports multiple backend engines and does not lock you into one ecosystem. Now, what do I exactly mean when I say that Keras supports multiple backend engines? Well, Keras is basically a high-level API, and this high-level API can run on a lot of low-level APIs such as TensorFlow, CNTK and Theano. So now Keras is what works at the front end, and at the back end you have either TensorFlow, Theano or CNTK running. Right. Now Keras also has a strong multi-GPU support. So when I say Keras has a strong multi-GPU support, what I mean is you can basically divide the data or you can basically train the data on multiple GPUs. So let's say you have an input data which comprises of 100 records and you divide into 5 mini batches. Now you can train these each individual mini batches on separate GPUs. So let's say you have a model and you have the input data. Now you'll be making copies of this input data and each individual copy would run on each single GPU. And each of that GPU would give you an individual result which is aggregated and you'll get the final result. So this basically speeds up the model building process. And Keras development is also backed by all of the major companies out there such as Google, Amazon and Nvidia. Right. So now that we've understood why should we use Keras, let's actually understand what is Keras. So as I've already told you guys, Keras is basically a high level API and it is written in Python. And this high level API can run on top of Theano, TensorFlow or CNTK. And it is very easy to work with Keras. So you have individual modules and you can invoke each of these individual modules to keep adding layers on the neural network. So it is as easy as that to work with Keras. So now that we understand what is Keras, now let's have a look at the different models in Keras. So there are basically two types of models available in Keras, which are sequential model and functional model. So let's start with the sequential model. So simply put, sequential model is just a linear stack of layers. So you have one layer, on top of that one layer you add another layer. On top of the second layer you add the third layer. On top of the third layer you add the fourth layer. So it is basically a sequence of layers. So as we see over here, this input layer would be our first layer, and on top of this input layer we'll add the first hidden layer. And on top of this first hidden layer, we'll add the second hidden layer. And finally, on top of the second hidden layer, we'll add the output layer. So simply put, a sequential model is just a linear stack of layers which processes the data and gives out the final output through the output layer. Right. And this is how we can invoke a sequential model through Keras. So first we'd have to import sequential from keras.models, and then we'd have to import whatever layers that we require. So the first step in creating a sequential model would be to create an instance of this. So we have to use the sequential method and we'll create an instance of it. So now that we've created a model, so with this model we can keep on adding layers. So what we are basically doing is, for this instance, I am adding the first layer. So this first layer is basically a dense layer and it comprises of 32 nodes, and the dimension of the input which this first layer takes is 784. And we are also adding an activation function to this first layer. So it is as simple as that. First, you create a model, and then whatever layers you want to add, you can just add it with the help of the add method. So this is how we can create sequential models in Keras. Now we'll head on to the second type of models, which are functional models. So functional models help us to create complex models. Now, the problem with sequential models is you can give inputs only at the beginning stage over here. So let's say if I want to add new inputs for the second layer, that wouldn't be possible. So once if you give the inputs, you cannot add anything else in between. So this is where functional models differ. So in functional models, it is not necessary to follow the same sequence. So when it comes to functional model, any layer can be connected to any other layer. And these three steps which you see, these are the three steps which have to be followed to create a functional model. So we start off by defining the input. And once we define the input, we start off by building a set of layers. And these layers can be connected anyway. So I can connect the first layer with the fourth layer or the second layer with the 10th layer. So I start off by defining the inputs and then I'll create the layers and then I'll connect those layers. Now finally I will build the model. So these are the three steps involved. First, define the input. Second, build the layers and connect the layers, and then finally build the model. Right. So let's understand each of these steps properly. So when it comes to a sequential model, we actually have to create and define a standalone input layer that specifies the shape of the input data. So as you see over here, we are importing input method. So from keras.layers, we are importing input and we are defining the shape of the input data. And this is extremely important when it comes to functional models. So first, we have to start off by creating the input layer. And once we create the input layer, we can keep on adding other layers. So as we see over here, first we import input method, and after that we are importing the next layer, which is basically a dense layer. So as we see over here, first we create the input layer using the input method, and the shape of the input is 2, and I'm storing it in visible. After that, I'll add another layer. So this is basically a dense layer. Now, this dense layer has two nodes in it and it is connected with the visible layer over here, right? So we give out the name of the previous layer after we create the first layer over here. Or in other words, layers in functional model are basically connected pairwise. So this is the dense layer and this dense layer is connected with the first input layer, which is visible. Right, so we're done with the first two steps. So first we created the input layer and then we connected the rest of the layers. Now after that we have to create the model. So defining the model is extremely simple. So first we'd have to import the model method from keras.models, and using this model method, all we have to do is pass in the input and the outputs. So as we have already seen this before, input is the visible layer and output is the hidden layer. So we are passing these two layers in this method and we are storing this in the model instance. So this is how we can create a functional model. And Keras already has a number of predefined layers. So these are some of the predefined layers listed over here. So Keras can have core layers, convolutional layers, pooling layers, recurrent layers, noise layers, embedding layers, and so on. So it has multiple predefined layers associated with it. So now that we've understood the different models available in Keras, now let's understand some problems when we are building the model on top of input data. So the aim of model building should be to gain the maximum accuracy. But then again, it is not that easy to build that perfect model. Many a times what happens is our model is not able to learn the right amount of data. So let's take this case over here. So let's say we build a neural network model on top of this data, and our aim is to classify this data into two classes. So the first class would be this cross and the second class is the circles over here. Now the problem with this model is it has not learned all of the features of the data properly. And since it has not learned all of the features of the data properly, the misclassification over here is quite high. So these three circles, which should actually be circles, have been classified as cross. And these crosses which you see, they have been misclassified as circles. And this misclassification is due to the underfitting of the model. So I again restate it. So underfitting of the model basically means that it is not able to learn all of the features of the data properly. And when it doesn't learn all of the features of the data properly, it is not able to predict or it is not able to classify the problem in a correct way, or it doesn't give us the perfect accuracy. So let's say if this model is built on the train set, then the train set accuracy would be somewhere around 65% and the test set accuracy would be somewhere around 63%, which is not really that good, right? So this is basically the problem with underfitting. Now, instead of drawing a straight line, what if I make the model a bit more complicated? So what I'll do is I'll build a polynomial curve over here. So this is a complicated model. So this complicated model is better than this model over here. So this model gives just about the right fit. So over here, all of the circles have been classified correctly as circles, and just these two crosses have been misclassified as circles. So let's say this gives an accuracy of around 95% on the trained data and an accuracy of around 93% on the test data, which is actually good enough. Now, what if I get over enthusiastic and build a very complex model with lot of polynomial variables in it? So this would give me a curve something like this. So over here, all of the crosses have been classified into one pool and all of the circles have been classified into another pool. So this basically gives us 100% accuracy on top of the train set. But the problem is it fails miserably on the test set. So the problem actually is that it fails to generalize. So when it is given the train set, it learns all of the features of this train set perfectly. And when it comes to the test set, it has not seen the test set at all. And that is why it fails to perform properly on the test set. So when it comes to the train set, it gives out 100% accuracy, and when it comes to the test set, it might give only around 75% or around 80% accuracy. So that is why underfitting and overfitting should be avoided, and we need to find that appropriate fitting or just the right fitting to get that ideal accuracy on top of the test set. Right, so this graph over here explains this in a better way. So we have error on the y-axis and model complexity on the x-axis. As we see over here, as we keep on increasing the model complexity, the error, it decreases for the training set. But what happens with the test set is, as we increase the complexity, the error first decreases, but then again the error increases as we keep on increasing the model complexity. Right? So to get that perfect accuracy on top of the test set, we need to find out that optimal model complexity. Only when we find out that optimal model complexity, that is when we'll get the maximum accuracy. Right. So now that we've understood why overfitting is harmful for a model, let's understand the solution to it. So the solution to overfitting is basically regularization. So there are some regularization techniques which help to reduce overfitting. So let's actually take this example over here. So here we see that we've built a very complex model and it learns all of the training data perfectly. But then again, since it learns all of the training data perfectly, this leads to overfitting. Now, the solution to this would be regularization. So when we apply a regularization technique on top of this data, what happens is it penalizes the weight matrices. So when it penalizes the weight matrices, so the values of those weight matrices and bias matrices would change a bit, and this would lead to a less complicated curve. Now also we need to make sure that we give the appropriate value for the regularization coefficient. So if we keep the regularization coefficient to be very high, then what might happen is some of the weight matrices would become 0. And when some of the weight matrices become 0, it would basically lead to a model which is underfitting the data. Right? So again, when we are applying this regularization technique or when we are tuning this regularization coefficient, we have to make sure that we don't alter the weights too much. And if we alter the weights too much, then we might end up actually underfitting the model. And that is something we have to avoid. So that is why we have to find out that right value of regularization coefficient which would give us this appropriate fitting. So we don't want a model which is too complex or too simple. We just want that right fitted model which is able to give us the perfect accuracy on top of the train set as well as the test set. Right, now let's actually see some regularization techniques. So one regularization technique could be to add dropouts in our neural network model. So now the question in your head would be, what exactly does a dropout do? The dropout basically means that we randomly remove or cancel some nodes during each iteration. So as we see over here, in the first layer, these two have been dropped out or these two have been removed. Similarly, in the second layer, these three have been removed, and in the third layer, these two have been removed. So this again is an arbitrary choice and we can give any random value to each of these layers. So now that we know what exactly dropouts are, let's understand how they are helpful. So when we cancel out these nodes during every iteration, they do not memorize the data. And when they don't memorize the data, this actually in turn helps in not to overfit the data. So let's actually understand this through an example. So let's say we have this training data and we are building this model on top of the training data, and this training data goes through 3 epochs or 3 iterations. So in the first iteration, in this layer, these 2 are cancelled out. In this layer, these 3 are cancelled out, and in the third layer, these 2 are cancelled out.
Just a quick info, guys. Test your knowledge of computer vision by answering this question. Computers process data into information by working exclusively with which of the following? A. Multimedia. B. Words. C. Characters. D. Numbers. Comment your answer in the comment section below. Subscribe to Intellipaat to know the right answer. Now, let's continue with the session.
Now, this is only with respect to the first iteration. Now, in the second iteration, again, a random set of 2 nodes would be cancelled out. And it's not necessary that these would be those 2 nodes. So, those 2 nodes could be either this one and this one, or this one and this one. So, it could be any random combination of 2 nodes which are cancelled out from this first layer. Similarly, again, from this second layer, a random combination of 3 nodes is cancelled out. Again, in this third layer, a random combination of 2 nodes is cancelled out. Again, we'll come to the third iteration. Again, the same thing happens in the third iteration. So basically, adding a dropout layer works as an ensemble model. So every iteration gives slightly different model. So in the first iteration, we have different set of nodes which are giving the output. In the second iteration, we have another set of nodes which are giving the output. Similarly, in the third iteration, we have totally different set of nodes which are giving the output, right? So a dropout layer basically works as ensemble models through each iteration. So we can basically set a probability of number of nodes to be dropped out. So over here p is equal to 0.5. So this means that the dropout percentage would be 50%. That is, we'll be keeping 2 nodes and we'll be removing 2 nodes. And it's extremely easy to add dropouts with Keras. So first we'd have to import the dropout method from keras.layers.core. So once we do that, we'll build a model, and in this model we are adding a layer over here. Now for this layer, for this dense layer over here, we are adding a dropout, and the probability of the dropout we are setting it to be 0.25. So it's as simple as that. So all we have to do is use this dropout method and set in the probability of dropout. So adding a dropout layer was one regularization technique. Now we also have another regularization technique, which is data augmentation. So the simplest way to reduce overfitting is to increase the size of the training data. Now, how can we increase the size of the training data? Well, we can basically modify the data to increase the size of it. So let's say we are dealing with images or images of these numbers over here. Now in this case, what we can do is we can augment the data. So let's say I have the input data, which is basically image of the number 2. Now if I want to create a duplicate of this image, what I can do is I can add some sort of transformation on top of it. Let's say the initial image which had the number 2 was over here at the center. So instead of keeping it at the center, what I'll do is I'll move it up. Similarly, let's say if I had the number 3 over here in the center, I'll move it down. Similarly, over here, the number 3, I'm pushing it to the right. And not just moving them to the top, bottom, left. We can also flip the image. We can also scale the image. So let's say this is my input image 7. So instead of keeping it like this, what I'll do is I'll flip it inverted like this. So I'll flip it and it'll be inverted. And also I can scale it up, or in other words, I can also increase or decrease its size. So these are different transformations which I can apply on top of the input data, so that I can create more records, or records which are similar to the original records. So let's say if my input data consists of images of the first 100 natural numbers. Now if I want 1000 records instead of 100 records, all I have to do is add some sort of transformations on those original records and have records which are pretty much similar to the original records. So this is how we can augment the data. Now, what is the importance of data augmentation? Well, when we have more data, obviously it'll be difficult for the model to learn all of the features of it. So when we have less training data, then it is very easy for the model to overfit it. And when we have a lot of data, the model will obviously take a lot of time to learn all the features, and it is difficult for the model to overfit it. So this is how data augmentation works. And when it comes to Keras, we can perform all of these data augmentation strategies using the image data generator method. So we'll have to import this image data generator from keras.preprocessing.image, and it has a big list of arguments. Such as over here, we are setting the horizontal flip to be equal to true. So similarly, there are a lot of arguments which we can play with.
Okay, first step what we're going to do is we are going to learn that how do you augment your data or how do you increase your data set if you have less amount of data, right? So we learned that we have only 200 images of each category, and that is not good for building a model out of it, right? We are going to augment our data. Until then, let me show you that we have this data set. And okay, before showing you how do we get this data set, you all can also get it. Just this was a Kaggle competition, cat and dogs. You can download a data set from here. It's quite easy. Just go on this. Okay, everybody has an account on Kaggle, right? If not, then now, just now create an account, right? While you are listening to the class, just create an account also. So this competition started almost like 5 years ago, if I remember. Yes, 5 years ago. And they made the data set, and this is like one of the benchmarks to start with deep learning, when people say. So people have done different things. And okay, before we even start with this problem, let me introduce you those who don't know Kaggle. Kaggle is actually a platform for data science, ML, AI competitions. Kaggle, what it does is that it is in collaboration with very big, large corporations like Walmart, like Google, Facebook. So these people, they are ready to give their data, but in return, they want that if they are hosting a challenge, they should come up with a solution also. So what Kaggle does is Kaggle collaborate with these big corporations. Corporations give them the data, and then they host a challenge out of it. Challenge multiple people from all over the world. They come together and they solve the problems through this, right? So Kaggle is not just only a data solving platform, but a collaboration platform also. You'll come to know what multiple people read their problem statements, see their solving approaches, how do they solve. And second is that companies are also like learning new things from here. What they're doing is they're seeing people, okay, you are performing well in Kaggle, it means you're a good data scientist, you're hired. So I know two or three of my friends who got hired just because of their Kaggle profiles, right? So always maintain a good Kaggle profile, start working on this. On the Kaggle problem, at every problem you will see these 6 tabs. The first one is the overview where we read about who has given the data. This is a petfinder.com. I think petfinder.com, they started a new competition almost like 2 months ago. So yeah, participated in that. So actually, petfinder.com is a Malaysian NGO for pets. What they do is that they try to help veterinary help to all these animals. And in the recent problem, they were asking this thing that how can one match the adapter and the animal. So what this NGO does is this NGO take care of animals, and then they give this animals to whoever wants to adopt animals, right? So they want to match the profiles. Which adapter will take which animal, so that they can propose him or her at the very first instance. That was the recent problem, and that was classical problem of NLP plus image. You should try this. This is a very old problem. This is a benchmark problem. Second tab comes under the data tab. Here you can come on this tab, and it's a very important tab. People generally miss this tab. It is here where this thing is written. So multiple people, they have come up to me and they say, okay, how do I know that this is a so so when you download this data, they will give you all the images. Now you have got the images. How do you know which one is cat and dog? So they have written here that in your dimensions that you'll see that all the image names have a label inside them. So the image name would be cat dog some number dot jpg or dog dot some number dot jpg. While you're training, you should keep 1 for dog and 0 for cat, right? Second is all terms and conditions, but okay, you can click here, download all, and it will download a dataset for you, right? I think displays, okay, this doesn't display because this is an archive file currently. Otherwise, you might also see the photo here, right? So you can download the dataset by clicking on this button called download all, right? Then second thing is this third thing is this kernel thing, very important thing. So what this kernel is actually is that all the people who have worked on this cat and dog problem and they want to share their code, they share their code here only. So you can read, okay, it says CNN cat dog classification, Keras 1, Keras cat and dog classification. So people, they do different things on this, and you can read their kernel, right? If you click on this, it will open a Jupyter notebook for you inside Kaggle only. So those who are not aware, Kaggle has been bought by now Google. Google bought Kaggle in 2017, yes. And now so this is all Google running behind. Okay, so you can see, okay, see, this is a notebook, right? This notebook has opened in front of you, and this guy is, his name is USIMIT. You can see his code, whatever he has run, and what things he's trying to say, right? So see, you can put anything, you can put images, plots, code is one thing that you're putting, right? He's putting callbacks, early stopping, reduce, on plateau. Okay, so all the code you can see right here, right? He's also producing some good graphs, right? So you can read all these things here, you can do whatever you want. Okay, this is a very good feature of Kaggle. I think this is the best way. How do you contribute it? Discussions, if you have any problem or people are telling new approaches, people they don't want to share their code, but they have something that they cannot write in code, but they can tell you, this is what people do here. People, they ask questions. I can't get data of competition, right? See, this is written here 2 months ago. I think something has happened here. Are they not allowing you to download the data? Okay, so one thing that they have written is that whenever you are making your account in Kaggle, just make sure you are verifying your account by phone number also. Sometimes it's idea also. Sometimes it's just general idea that people post on Kaggle only. But it's very, see, it's inspiration code. So it's, see, this is one of the biggest problem that new people do on kernel. What they want to do is, because they want to increase their rank, what they will do is they'll take the number one's code, they'll copy paste it, and they'll run. They'll get rank 2 on the public leaderboard, but whenever the private leaderboard comes, they fail, right? And this is the biggest problem people are doing. They just, so this code is for the inspiration. Just read the code, just get inspiration out of it, and then write your own code, right? At the end of the day, always you have to write your own code, right? So this is like your, see, now this guy on number 14, right? So this guy, he got a rank 14 on the public board, right? If you see, this is the public board, right? And then on the private board, he got -7. So these guys, they fail drastically. So never copy paste someone's code, right? And get inspiration, and that's it, right? uh, make your account on Kaggle, verify your account with phone number, and then download the data from here. Data, click on this, and then download all. To people who are working on Collab also, Collab, now you can install Kaggle through pip also. It's just one step, like pip install Kaggle, and then you can run this command on your Collab, and it will download the data set for you, right? Now let's move back to our thing that was of cat dogs, augmentation. How do we start doing augmentation on a dataset? Let's imagine that we have very less dataset, like very less. Let's do quickly our basic import Keras, import NumPy, import OS, pwplot as plt. Okay, so just to check what is my version is 2.2.0. Okay, let me take you to data path. I will be using the relative path. See how I move back, and then I say data, and then cat dog small data set. This will be my data set. Okay, let's take a test image. Test image is equal to okay, we forgot to import OpenCV, CV2, cv2.im read data path plus cat. Let me take one file example. So I'm just doing nothing. I'm just copy pasting the cat's name, file name, so that you can see it, right? plt.im show, and if I do test image, it will show you the image. So what I did here is I just said I am read unchanged. It means I am saying I am saying to CV tools that please don't change any kind of a color formatting. Just print whatever it is. Right? Okay. So it printed me this image. Now the challenge here with us is that we have a very less amount of data. We don't have a large amount of data. We have just very less amount of data. And this is just 200. Now how do we increase the data set? Now one of the options that you okay, before even I tell you something, let's say that I give you an example that okay, this is cat dogs, you have to build a model and you have just 100 images. What kind of approach you will use to first of all increase your data?
Just a quick info, guys. Intellipaat provides artificial intelligence online training mentored by industry experts, the course link of which is given in the description below. Now, let's continue with the session.
You have to just increase the data, nothing, do nothing, just increase the data. Now let's say there is a very small kid, right? He's like just a year old, right? And you are showing him a image of cat, the top view of the cat. Now imagine the top view of a cat, how it will look like. Let me check if I have an image of top view of a cat. Okay, you can do a Google, right? Why are we doing it? Let's say that you show this image to that child and you show it multiple times, like 10 times, and you just say this is cat, this is cat, this is cat. Right? Now the child, he has understood, okay, this is cat. Next time if you are going to show him this kind of an image, he will say, okay, this is cat. Yeah, I know this is a cat. Okay, I understand this is a cat. But next time, if you show him some, okay, now if you show him this kind of a image, he'll get totally confused, right? Because he hasn't learned this thing that cats look like this. He only learned 10 times, and that too with a confidence. See, whenever you show someone one image and then say this is a cat, he gets okay, this is a cat. But when you are showing it 10 times and then saying it is a cat, his mind learned this thing that okay, this shape, top view, this thing is called cat. Irrespective of learning about its feature, now it is mugging up the things. It is mugging up that okay, this is a cat, this is a cat, this is a cat. Next time if you show him some generic kind of a picture like this or this, he'll be like, no, this is not a cat. Definitely this is not a cat. A cat is something where you see the top image and then that is a cat. This is not a cat. This is the problem when you do a copy paste, right? Whenever you're doing a copy paste of 10 times, what is the thing that is happening to you is that you are showing the exact image 10 times problem. That's why there comes a new and a handy thing that helps you. That is called data augmentation. Then the second thing that break the images if it has multiple cats. Okay, I understand. Break the image if it has multiple cats, we can do. But if it is a single image, then we can do nothing, right? No, still we can. Still we can. This is called data augmentation. See, now you cannot produce new kind of data, right? So this is a simple example of cat. So what you can do is you can just go to Google and download multiple images of cats, right? But let's say this is some kind of a business problem and you are dealing with something that is not available on internet. How will you increase the data set? This thing is called data augmentation. Now, data augmentation, it involves two kinds of knowledge. One is the domain knowledge, that you need to understand that what kind of a image you are using and what kind of a problem you are dealing with, right? So we are dealing with cats. Okay, so first of all, how do you do data augmentation? Then let me show you this thing. Okay, so for data augmentation, you will use Keras. Keras has already given you this thing from keras.preprocessing.images import image data generator. Now this image data generator will generate images for you for the image that you have given, right? Now when I say, let's say we make a data generator, see, one thing that I might have already told you, if not, then I'm sorry, that everything that starts with a capital thing in Python, and especially if you are working with a standard library like Keras or TensorFlow, that is a class, right? It's not a normal function or a normal method, it's a class. So you have to first initiate a class, right? And then you can work on it. So image data generator, if you see its help here, if it is visible to you, this block How did I bring this tooltip? Shift tab is the thing that helps you to bring this out, right? So whenever you are working in Jupyter Notebook, just make the function, just go to it and then just say shift tab and you will get this. Okay. So image data generator, it says, its docstring says that it generates batches of tensor images with data with real-time augmentation. And the data will be looped over in batches. Okay. So we get this small idea that some kind of a data augmentation is going to happen, but it has two things. It is going to happen in real time. Second, it is going to happen in batches. So it's not like you have given it a folder and it will take all the images. No, it will take only some amount of images, process them, give it to you. Then the second batch, process it, give it to you. Third batch, process it, give it to you. This batch will happen until your images are exhausted, right? Now, when we come to the options that are available in image data generator, these are like multiple options: feature wise centering, sample wise centering, feature standard normal. So first of all, before going to this complex one, let's go to simple one. One is called the rotation range. Now, see, one of the, if your business case allows you to rotate your image to certain angle, then you can use this. Wide width shift range. It means if your business use case allows you to shift your images to a left and right on the width basis, you can do. Similarly, for the height up and down, you can do. Brightness you can change of the image. Shear range you can change the image. Zoom you can zoom into a little bit into the image. Now, when I'm saying your business use case is allowing you, what does this thing mean? Business use case is allowing me. It means that, let's say, okay, let me ask you this question: can I flip this image uh, on a horizontal basis? It means if you keep a mirror here, can I just, okay, now but if I say, and let me say that if I put a mirror down here, now I will have a, now let's say that I put a mirror somewhere here and I will have a image over somewhere here. Now the cat will be somewhere like this with ears here and looking here, right? Now, does this make sense to have this image inside your data set? You want to keep all the bad images away from the model, right? Only good images, real world images, right? You don't want to set wrong expectations out of your model, right? Rather than giving him, I think giving small data is good rather than giving him false data and doing a overfitting over the model, right? Because see, if you're testing, your training accuracy is 87 and your testing is also 87, it keeps a low expectation inside in front of a client also, right? So the client also knows, okay, training me 87, then I can expect testing also 87 or 85, right? But when you overfit your model and then you say that, okay, my model is like 97 and then you deliver somewhat like 68, it, that time, that's a real pain in front of a client, right? So always try to, so what they say in industry is that what do they say, that under expectation and over delivery, right? So you put your model somewhat like, sir, we got a training accuracy of just 85, but now testing me when he gets, he's at like 92. That's when he gets happy, right? If you deliver both as 92 and he's getting 92, he never gets, the client never gets happy, right? So it's all about how do you frame your business problem, and then you want to model your you want to train your model, right? So this is how you do augmentation in Keras. Let's do it. So see, Keras is one of the good libraries. Everything is totally sorted. So when I want to do some this image augmentation, I know this is a pre-processing kind of a thing. So I'll just say, so I don't have to remember all these things, right? From Keras dot pre-processing. Now pre-processing has multiple things. Let me show you all these things, then it will be a better thing. Okay, so my question was simple, that okay, how I see that what kind of pre-processings are available to me at this particular instance when I've written from Keras.preprocessing. How can I know that there are more, what are the different pre-processing available to me? So you know that these are the different kinds of pre-processing that are available to us. And then once you have written import, then can I do something to get all the things options? Again, a tab. So you get the second thing, image data generator, right? So you have an image data generator. We need three more things. One is called array to image, then image to array, and load image. Load image is actually a feature from Keras that helps you to load the image from a directory. Okay, I'll say OpenCV PIL. CV2 is open image, right? CV2 is OpenCV, right? So OpenCV, SK image, and then PIL or pillow, whatever you say, and then Keras. Keras at the back end is using pillow and PIL for using. So whenever you're using load image, it is actually using the PIL module to load all the images, right? Let me do one thing. How do you start? You have to define your data generator. You say image data generator, and then you have to say what kind of a different augmentation you need to choose, right? I am going to choose a rotation range. I am going to rotate my range till 40 degree. I am allowing it to change it. Second, let me say I want to do a width shift. Width shift, let me do plus zero point 0.1, right? Similarly, for height width also, I want to change 0.1. I can do one more. I can do like horizontal flip that we were discussing is equal to true. Okay, this CTM is coming in the row. This horizontal flip, or I can do some shear zoom. So these are all the things that I've done in data generator. You can just type in data gen to get to know all the things that you have done. Let's say that we did shear change. If you want to know what it is, you can get through this, right? That has become, it's in the constructor of the func on the class, it has written, and it becomes the feature. So you can later also know that what kind of a properties that you have used. And if I do this, you can get all your properties also. So what we have done till now is that we have created a data generator. We have just told the model that these are the things that we want to do. Let's do this. Let's create a test image. Let's create an image. Image is equal to, we'll say load image. Load image from where? From data path. Plus, let's say we do it for cat dot. Okay, let me search for a good cat. Cat. Okay, I don't even. Okay, let's do this one only so that you get more view on this. This is 38. Cat 38 dot jpg. So see what it has written. Let's check that image load image will not return you the you will not return you the np dot array matrix or matrix, right? It will return your PIL. So what you have to do is you have to say that image img to array, right? And then you have to pass your image inside this. This will convert your PIL image into your matrix numbers, right? And CV2 was directly giving you this matrix. Remember, when we loaded our image through cv2.im read, it was directly giving us this matrix, right? So there's a difference. Always use which library to use for which instance, right? Now what we can do is, let's say image is equal to image.to array. Now I got this image. If we check the shape is 337.350.3. Okay, it's all clear, right? Now I have the image also. If I can do a plt.im show, it will show me the image. Clipping input data to valid range with im show with RGB for float points integers. Okay, so what has happened is PI has returned this thing with dot min. What they have done is they have returned something larger than expected. Okay, so they are actually in floats. That's why PLT is not showing you. PLT believes in just, it is there, right? So what PLT assumes to get only integers, but we were returning a float. We were returning a float, but with integers only. We were just saying 3 co as 3.00. PLT has some issues with the floats, so it only expects you to give integers. So just convert it into integers. Okay, so this was the blank image that we have, original image till we have. We have not done any kind of augmentation to it, right? But now do you remember that when we were doing this image generator, it said that the data will be looped over batches. So you have to make batches of the image. It will not just take single image, or even if you're giving a single image, just give it a batch, right? So what we have to do is I have to reshape this image with the batch also. So I will do nothing. I will just say image.reshape.image.reshape 1 comma and image.shape. Okay, rather than doing this, I will just say image.shape.
Just a quick info, guys. Test your knowledge of computer vision by answering this question. A string of 8 zeros and ones is called what? A. Megabyte. B. Byte. C. Kilobyte. D. Gigabyte. Comment your answer in the comment section below. Subscribe to Intellipaat to know the right answer. Now, let's continue with the session.
This will work for us. Right, so what I'm doing is I'm just adding one more dimension to the image. So now if you check the image shape, I have done nothing but I've added one more. So it is saying that this batch contains only one image. Now we are going to start this thing. We are going to say for batch I'm going to call this data gen function and I'm going to say flow, simple flow my image inside you. And this is actually not an image, but this is a batch of images. In our case, it's only just one image, but it might contain 10 images or 20 images, right? And then whatever it asks you, it says first you have to give your X, then we have the batch size. Batch size is just one. We have only one image. And then it says save to dir. Yes, we can save to dir. Let's say I'll give it temp. Right. Next, what is it asking? It's asking for seed. No, seed is for like npc that you want to give, right? And next you can give it some prefix. Let's say kaggle hyphen comp, right? Hyphen leave it. And what next do you have? You have save format. You can tell it which format do you want to save. Let's say JPG, right? These are the things that you want to start in a data generator.flow. Now I want to stop this also because this is not going to stop until and unless this thing happens. So what I'll do is I'll say index and then I'll say enumerate. So enumerate, what it does, it will also tell you that how many times your this for loop has run. So I'll just put a thing that if index is like is greater than 30, then do a break. Okay, it says file not found. Which file not found? Okay, so temp folder is not there actually. Oh, okay. So I have to create a folder. Let me go there. Temp there. I made a folder called temp. You can see I made a folder here. You see on the screen on the left hand section, I made this folder called temp. And I have given it here, save to directory called temp. And now if I open this directory, if I expand this, I have lot of images. Let's go and check it. If I go to the folder and if I go there, temp folder is here, right? Every one of you can see this folder, temp folder. I go inside this temp folder. See, for that particular one image, you have now these images. Now, just think in terms of numbers. Now, does this look like the same metrics that you got in the original image? Okay. Yeah, see, they are different, right? Now, don't think in terms of image, right? For you as a human, this is still an image, right? Just think in terms of numbers, that matrix that you got in 370 into 520 into 3 channels. Now, do you really think the number are going to be same? So just for one image, we got like 20 different combinations with like 5 to 7 things, right? So this is how you can like do these things out, right? And then see how convenient it is. Like it tells you that what do you want to give it a name, like Kaggle underscore something something something, and then you want to like give it some name also. So it is giving you like everything inside there. This is how you can do these things. But the most important thing is that what kind of images you can provide to the directory. right? You can give it PNG, you can give it JPG, you can give it DMP, you can give it TPM and TIFF. If you are giving any other kind of image, no, 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 please don't give, right? You have to abide by the rules that these are the only images that you have to uh, get inside, right? Next thing is the target size. Let's say that you, because your images are of different dimensions, and we saw this in last problem also. If you guys remember, we were having this problem that our data had images of different dimensions, and this was the plot that we got. For height, we had this thing, right? So we came to know that 350 was the median height that everybody had, but our height ranged from 100 to 500. And similarly in width also, our range was from 100 to 500. So what we had to do, we had to somehow come up with a mean height and mean average, and then we have to convert our height and shape into some constant things, right? Remember? Now here, let's say you don't want to do all these thing headaches. What you just simply say to the model, the flow from directory, you just say to him that, okay, this is my target size, convert all my images into this size, 256 cross 256 or whatever you want to give, right? By default, if you're not giving it anything, it will convert the images into 256 into 256, right? Then you can give a color mode also. Let's say that your model is, you have a lot of images and your model, I mean, it's a very small, your images are too different from each other, and you don't want to take all the data of three channel, you just want to make it into a grayscale also. You want to make a grayscale model and you want to read the images into grayscale. Don't worry, just tell it to Keras, just say that, okay, my color mode is RGB or grayscale or RGBA, whatever you want to give, just give it, right? That's all. Now you might ask me this question, what is this RGBA? RGBA means that this is a 4 channel image, red, green, blue and alpha. Alpha channel is also known as the transparency channel. See, if you're dealing with images, you have to know everything about images. So I'll tell you my case. I was working with this client who wants to know that whenever someone is uploading an image, he is not uploading a copyrighted images. Now this is a now this is one of the very serious problems, right? And this is like everybody is facing this problem, right? Let's say that you have some e-commerce store, and what people generally do, rather than taking the own photo, they'll take someone else's photo, like stock image photo or some image photo, and they'll upload it. Now when the user uploaded a photo on your platform, he or she doesn't care this all this thing, right? But stock image will see, he'll get you. Why is my photo on your website, right? Why is my image on your website? He'll catch you, he'll sue you, right? So this is a very practical problem that people are dealing right now, that they should not have someone else's copyright image in their database, right? So this is the problem that they're dealing now. I was given this task. Now, how do, and this was like in very like 2013, if I remember. So this image has a property that is called transparency channel. Now, transparency channel means if you set this transparent to 100%, that means you can see everything. And if you press transparency to 0 or opaque to 100, it means that you cannot see anything. So whenever they want to copyright an image, what they do is they add one more layer of transparency, and on that transparency, they have their copyright seal. They have their copyright seal, signature, whatever they want, and then they put it, right? If you want to differentiate between a copyright image and a non-copyright image, you have to provide your data set. Now, at that time, if I would have read this image normally, like RGB, then I would have never read the copyrighted logo on this. I wanted my model to learn that how are the two images different, right? One has a watermark and one doesn't have a watermark, right? So that's why I had to read both the things. And this is how you do. You read your color mode as RGBA, and this way you're telling your model to read the image with a alpha channel also. And it will read it and it will help you. Right. Then the fourth option comes as the classes. Now let's say that this is actually an optional thing, but you should tell your model that how many classes do you have, and then based on that it will look for other things also. Let's go to one more thing, that is class models. So class mode means that, is it a binary kind of a categorization or it's a categorical kind of a categorization? Binary means that you're just looking for like one category, true and false. Categorical means that you're looking for more than two or more than two, like cat, dog, elephant, whatever, right? Binary would have been the case where you say dog or no dog, right? Cat or no cat, right? Then you have some sparse categories also, where you have some less and then some unbalanced categories also, right? If no labels is yielded, then it will take batch size. Now batch size is one of the important size. Now you are telling your model that how, if you want to, let's say that you have 100 images total, then you are telling your model that batch size means 25. It means that it will create 4 buckets for you, each of size 25 for you. 25, 25, 25, because 25 when added 4 times will become 100. That will become the total number of images that you have in your data set. Make sense? Okay. Then you have this thing called shuffle. Now this is a very important thing, right? So in my case, when I was doing this thing called to identify if this image is a watermarked image or not, at that time I have to feed the image one by one to the model. And when I say one by one, I mean one image not copyrighted, second image copyrighted, so that the model can learn that okay, this is the difference between the two images. These are same images, there is only a small copyright logo on the left right section. So my model learned this. If imagine I would have shuffled my data set, like one image randomly is going with the other one's copyright image, then it would have made no sense to me, right? That's why always remember shuffle yes or no, depends on your, right? And then this thing is seed. Seed, you always remember np.random.seed that we did, right? np.random.seed ensures that what kind of a randomization you are using. Let's say that you are doing a model benchmarking and then you need to do, so all your randomizations are now constant on your particular laptop if you provide a seed, right? Save to dir means, let's say that you don't want to do it on the runtime. And when I say runtime, I mean that your model is running, your model is doing the training. At that time, Keras is doing all the augmentation, giving the images to the model. That's it. It's not saving somewhere until and unless you give this thing, save to dir. Save to dir. Then you have this thing called save prefix. Then you have save format that we just saw right now, right? Then we have follow links. Follow links means that there are like some symlinks also. If you're working on Linux or Unix, symlinks are like soft links. If you want to go inside of the data also, this we're not doing. Then we have subset. Let's say that you have done the augmentation, but you want to do it on the on your validation data set also, right? Now, sometimes people want to do it on validation, sometimes not, right? Sometimes people just say, no, I am going to validate it only on non-augmented dataset only. And it's fine. Sometimes business case thinks that, okay, no, validation should always be done on non-augmented. Augmented images are not the real images, so they don't do it, right? So it's up to you what, if you want to do it on training or validation, you can just provide it. There's this thing called validation split. Validation split means that whenever a batch is going and you say validation split is 0.2, it means that 0.2%, I mean, if out of 10 images, 2 images will be kept for validation and you will get the validation score also out of it, right? And then you have interpolation. Interpolation is again a different kind of a thing that you want to have a nearest kind of a, so whenever the image is loading, there are like different things that you can put in, like nearest color or binary color or bicubic color, whatever color target you want to do it, you can just change it, right? It's it's just a resampling of the image. So whenever you are doing a resizing, whenever you are giving this thing called whenever you are giving a target size, it means that you are wanting your image that is from the original type to be reshaped into this thing, right? 255.256.256. Now reshaping is again a very complex thing. We if you imagine it mathematically, then it's very complex, right? And don't compare resizing to rescaling or cropping. Cropping is simply deleting the image, right? We are not deleting the image, we are resizing the image, right? So resizing has different kinds of algorithms that you can use. They're like bicubic, nearest, bilinear, all these things you can like put it, right? If you don't, it's like always a by default thing that is always you have the Keras, right? Now what is the return thing that you are getting, right? In our example, what we did was, in our example we did this thing called save to dir. So whenever you are doing to save to dir, it is going to save it inside the in your directory, whatever you have specified. Let's say we didn't specify that thing, then what is it is going to yield? It is going to yield two things, a tuple of two things, x and y. And it says that x is the numpy array that is containing a batch of images with shape whatever you have given, and y is the numpy array of the corresponding labels, right? Now you might think that we have not done the training till yet, and how it is giving the labels, because you specified it, right? And I told you that I'm going to tell you in like 5 minutes that how you should give the directory. Right now it comes the important part. Let's switch that to our folder where we have all the images. Whenever you want to read your data through generator, always remember that you have to start like this. First of all, create a parent folder. Let's say I created a folder called data generator small. Now this folder will contain folders, not the files. This folder will contain all the categories in which you want to divide your data. So in our case, we have only two categories, cat and dog. So what I did, I created two folders, cat and dog. All the cat images are inside this folder and all the dogs images are inside this folder, right? And to Keras, you will give the path till here, data generator small. Now Keras will go inside this data generator small folder. It will see, okay, so the user has given me two folders. It means that it has only two classes, cats and dogs. And then it will read all the images from cats and images from dogs. So now what you have done is you have read the images and it will give you, okay, cat means 0 and dog means 1 from here, right? It is not necessary to name your folder whatever you can name it. This is just for Keras to know that which category is inside which folder and which category is inside which folder, just for the knowledge of Keras. Let me show you the example. Let's go back to our Jupyter notebook. Simply let's say nothing, but the first thing is the directory. Directory is data path. I think data path is it? No, I have to change it. Let me type it statically. I will say data and data generator small. I will give it just till here. Nothing. Then you have target size. Let's say our target size is 200. Then next what we can do is, let me move it here. Color mode is already RGB, classes is none, class mode categorical, batch size 32. Okay, let's change the batch size. Batch size I only want as 2. Only 2 batch size. Then we don't want to save it somewhere, we want to shuffle. Yes, we want to shuffle. We just do like this. Now what it is going to yield is, it is going to yield a tuple with x comma y. Let's see what it does, right? X and b is equal to y. And then we're going to break this. So it says, see, whenever you run this, it says that found 401 image belonging to two classes. Now, how did it know that there are two classes? Because he gave two folders inside this folder, right? So it doesn't matter whatever you give the folder name, no matters, but it just want to count that which folder belongs to which. It says 401 images, so one folder contains 200 and other folder contains 201 images. Now let's see what A and B brings to us. A should be a numpy array, correct? Okay, let me just type in there only so that it's for reference. And B should also be a numpy array, right? Very good. Let's just see the shape of A. 2 into 200 into 200 into 3. Okay, I'll take this one for the team. See, I told you that image data generator will always take this into batches. It will take it into batches, right? And it will generate batches of tensor images with real-time augmentation. In this time, our batch size was 2. What was the expected image that you want to get out? Was 200 cross 200, right? And how many channels of images do you really had in the starting? If you go and if you see, it's a 3-channel image. That simply means that this 202 into 200.200.3 means the first two is the batch size, second is the height, third is the width, and fourth is the channel, right? And shape of label means that because this thing yielded out two images, it is going to print the two labels of the images. Let's see what B is. B says the first thing is 101, and this is the one hot encoded return. It has returned it into one hot encoding. So I imagine that this is 1, so this should be a cat. Let's plot this plt.im show, and we want to just print the A's first image, right? This is not going to do because it's a float type, as type, int. See, it's a cat. And if I print the second image, it's again a cat. So this is how what the model has done is that it is on the real time basis. It has, but it doesn't. It has like augmented the image, and then it is going to give you. This was the method different from flow of a single image, right? Here you were converting, reading all the images on your own. Let me just type in here. Single image augmentation. Okay, and this is a flow from directory where I just said that read from the image and then convert it into thing, right? Now see, this is going to yield this is on a yield process. So it means every time it is going to give me a different answer. Let's say this time if I do this, there will be new images. See, it's a dog image. It's a cat image. And if you want to see, there might be a difference. Now, if this is a cat and if it's a dog and cat image, then it means that this time your see one hot encoding is different. The first one hot encoding is 01. It means it's a dog, and 10 means it's a cat, right? How do you use this particular data inside Keras also? I'll quickly again load the data path is equal to data and then dog cat. We have generator also, right? Where is the path? Here it is. Control C. Oh yes, we have. Okay, so we have data path I have set. Now this data path, I'll again show you this thing that this is actually how do you set this path. Very important. Please see that I have made a folder here called data generator small. Now this data, this folder responsible to contain multiple other folders which will be the categories of your model, right? And then inside those categories you will have different of your data sets, right? So you have to take the path till here only, data generator small. Don't go inside that, right? Now we can see here. I'll quickly do this augmentation thing from Keras dot pre-processing. Let's quickly make a data gen. Data gen would be image generator. If I do, let me do a rotation. Rotation range, let's say 20. Then you have your horizontal flip is equal to true. I won't do much. I'll just do this just because so that we get to know how we are doing this. Then we have data gen dot flow from directory, right? Now we know that this is going to flow from directory. I can just simply say data path, right? And it says that the data found 401 images belonging to two classes. Correct? We have only two classes and there are 401 images. Now let's quickly build up the data also. This is dense, this is flatten, and what else do we have? Okay, this is this. We'll add it later from Keras dot losses import categorical cross entropy from Keras dot optimizers import RMS prop, or we can use Adam, right? And from, or I think we should simply use the SGD also. And from Keras dot activations import relu, right? And next we need is softmax. This is all what we want. If you want, okay, we forgot the most important thing from Keras dot model import model, right? Let's quickly make a model. Model is equal to model, right? Model dot add. How do you start this? What will be the next one? Okay, Anybody wants to help me out here at which thing should be used next? Model.compile. Model.compile, you say that you have optimizer as SGD, right? Losses may you have categorical cross entropy. Matrix may you have accuracy, right? What else you can give here? Optimizer, loss, matrix, right? You have already given a lot of things. Then you say model dot. Now we do fit, right? This is what we do. You give your x underscore train here and then comma y underscore train here. But we don't have x and y something here, right? So that's why we have to do a small change here. This is the change. We will not use fit. We will use fit generator. Fit generator, you have to give it a generator. Your generator is data gen. Then whatever you can give is you can give. So you can give how many steps do you want to go per epoch, how many epochs do you want to go. Then if you have any validation steps, then you have class rates, and then don't use the workers as of now because you're not using GPU. So keep the use multiprocessing as false and workers as one only. Don't do much changes, right? If you're on GPU, then you can do multiple things. Epochs, let's say 10, and let's start this. Okay, this GTM is giving hard times. What does it say? You must compile your model before using it. We have run this model.compile. Okay, I got this issue. This issue is here. So this will take a input model.add, and then you have an input layer. Then you have an input layer. Input layer takes input shape as. So if you remember, okay, we didn't did one thing. You guys forget that we have to give it a shape also, right? So we have to give it a target shape also. Let's say we convert it into 200 cross 200, right? And then this is it. For the upper part, do we have something else that we're missing? Thing validation split. Let's do a validation split. Validation split of 0.2, right? Let's run everything again. Right, do this, do this. Okay, sorry. I have to fill in here 200 comma 200 comma 3, right? Now you do a compile, and then you do a model.fit. Okay, this time it's not working. Okay, so there are 10 epochs, and then how many steps do you want? See, now this is a very crucial question that it is asking is, now you understand this thing, what is a batch, right? What is a epoch, right? Sorry, first of all, epoch means that if you have, let's say here 100 images, then once you complete all your batches inside your total images, once these all the images have gone through the neural network, once in the forward and once in the backward, right? This is called one epoch completed. Now it's asking that in how many steps do you want to complete your epoch, right? So let's say that we want to complete in, like, let's say 3 steps, right? Because you have less data. 3 steps means that you want to perform your epoch into 3 cuts. So if you have total of 100 images, then 33 will go in first, 33 in second, and 34 in last, right? Do you get the concept of epochs and batches, right? Okay, now again it's saying something, image generator is not iterable. Okay, I'm so sorry. GTM, please go for here. Which version of Keras am I using? 1.2.0. Okay, this is one step ahead. Okay, so my Keras is a little bit ahead of you guys. I think your would be Keras 2.1.4. Mine is 2.2.0. So there might be some changes. Give me just a second. Steps per epoch none is not valid for generator type. So you have to give. Then it says image data generator object is not an iterator. Why it's not an iterator now? Sorry, my mistake, guys. So sorry. Okay, I was pushing this data generator object into that. You should like take the object out of this thing. You should take the return thing that is coming out of, and then you should use it. So this is going to run your model. You can see here your model is running. It will go till till 10 epochs, and you can see here it is written 3 out of 3. It means that your one epoch is taking 3 steps to complete one epoch. Now, if there are 401 images, how many images are going in one batch? 400 divided by 3, right? These are the number of images that are going inside the model. This is the only small change that you have to do if you're not doing the regular training rather than you're doing a batch training, right? Okay, there is one more thing that I wanted to add here is that there is this one step that is called rescale. Now, rescale means that you want to divide your all the images with 0.255.0. Why do we do this?
Just a quick info, guys. Intellipaat provides artificial intelligence online training mentored by industry experts. The course link of which is given in the description below. Now, let's continue with the session. Test your knowledge of computer vision by answering this question. Computers process data into information by working exclusively with which of the following? A. Multimedia. B. Words. C. Characters. D. Numbers. Comment your answer in the comment section below. Subscribe to Intellipaat to know the right answer. Now, let's continue with the session.
This is actually normalization, if you remember. This is normalization of the model images. That your image, the model should not look like that. There are some small images that are called 0, and then there are some big images called 255. So we normalize the data, we squeeze the data between some range of 0 to 1. And how do we do that? There are multiple ways of doing this. Standard scalar, min-max scalar, and this was the min-max scalar, where you divide your data with the largest pixel value. The largest pixel value that can come is 255. So you divide all your data with 255, and then you get your ranges from 0 to 1. Right? Correct? Makes sense? So this was a this was a small example. This was showing you that how do you connect your augmented data inside your model, right? This was all the step. So let's move to the next section of this thing that is called the CNNs. Now CNNs are actually a new kind of not a new, but they are one of the most fascinating kind of architecture that you will ever learn in deep learning, especially in images. So till now what we have done is we have just seen that okay, we are connecting some neurons to other neurons and other neurons to other neurons, and this is something the information is getting passed. And if you remember the maths behind this, that we are just doing a affine, then we do some activation function. It means that we are bringing some non-linearity in the data, and then we are passing it through some activation function, and then we are finally giving it to the next layer. And then this chain is going on. Things are coming in, going out, coming in, going out, coming in, going out, right? But how is this network helping the model to learn the key features, right? So today we learn this new and very interesting neural network architecture that is called CNN, or commonly known as the convolution neural network. So convolution neural network, what will it will do is it is somewhat like let's say if this is the original image, then to find out the features inside it, what you are going to do is you are going to take a smaller cube, or square, sorry, not cube. You will take a small green square, and then you'll apply this, you'll put this green here on the top. So it will somewhat cover like this, right? Then you will move this green spot to your right, right? Then one step down. So it will come like this. Again right, then one step down, then again right, then one step down, again right, and then one step down. Eventually this small image, or what we call it as filter, will like run over this whole image, and it will learn the important features and the aspects of the image. Right now, how does this done? I'll show you a very intuitive Let me make a new Jupyter notebook. See, this is somewhat what is happening inside your. So this green image that you are seeing right now, this is the big image, and the orange image that is moving is called a filter. So what you are doing is you are moving the filter on the image one by one. You are moving the filter by one. Now, when I say when you are moving this filter on the original image, what I mean is that you are doing a element-wise multiplication on this image, and then you are summing up all the things. So if I stop this thing here, okay, it doesn't stop. If I put it here, cool. I have this picture already with me. Control C. Okay, so img src equal to. Okay, see this image right now. Right, you can see this image right now in front of your screens. Okay, I'll push it here. Okay, so this green thing, this green image, and whatever this big thing is written here, these big numbers 1 1 0 1 1 1 0 0 1 1 1 0 0 1 1 1, all these big numbers are what? These are, let's say, the pixel coordinates of the big image or the original image, right? And then imagine this small, this orange filter, this orange filter where small red color me you can see these things, these numbers 1 0 0 1 0 1 0 and 1 0 0 1 1 0 1. These small numbers are the filter. These are the numbers for the filter that is going to move over the image, right? Now when this thing is moving over this thing, it is doing a element wise, or you can say a scalar multiplication. Element wise one by one multiplication means that this one is multiplied by one called 1 multiplied by 0 is 0, 1 plus 1 is 1, 0 plus 0 is 0, 1 plus 1 is 1, then 1 plus 0 is 0, 0 plus 1, 0 plus 1, and then 1 is to 1, right? And then you have one more. So all these numbers, first for this one, second for this one, third for this one, and fourth for this one. Sorry, this one. So these four, this number becomes 4, and you write here 4. Similarly, what you will do is you will shift the now this filter to a little bit of your right, right? Then you'll have the second one. If you move it to a little low, then it becomes your, see, low and down. It becomes 2 3 4, then 4 2 3 4. This is how your convoluted filters features are calculated. Everybody gets the idea. So now do you get the idea how this thing is coming? If you see this GIF a little more, once take your time, imagine how this thing is working. It goes on the right hand side one by one. One is shifting, goes down, again one shifting, goes down. And this is how your final image is made. This pink image is your final image that is made. Because now I'll tell you what is happening when you are doing this thing. So what is happening is right now here is that if you, so okay, just tell me this thing, that let's say if you are standing in front of something, right? And then, so how do you identify, how are your images identifying you as a body? I'll tell you. So there are pixel value that are changing at the border of your body, right? So let's say that you took let's say you're standing in front of a white wall, a pure white wall, and then you are standing. How are you differentiated from a wall? Because if you see, if you open up the matrix of that image, if you open up the numpy array of the image, you'll see that your body will contain a higher pixel values and the white wall will contain 0 pixel values, right? Now whenever your body to wall is there, whenever the boundary of your body is there, right, at that particular instance your pixel values will be changing, right? Because your pixel value would be somewhat like 230 235, and then suddenly the image of white will be 0, right? So whenever you will be running this filter over your image and then doing this multiplication, what will happen that it will largen up the broaden up the areas. It will broaden up those border areas for you. But this is his blog actually. So if you come down here, what is happening here is this is what the image looks like, right? We have already discussed this thing that 255 is sheer black and white is almost like zero, right? Now what is happening is, let's say this green was your image, this green thing was your image, and this orange one was your matrix, right? For your filter, right? What you're going to do is you're going to put this 3x3 image over this 5x5 image and then do a multiplication, right? Multiplication say you will be getting a convoluted feature. Right now, if you understand this thing, okay. So first of all, you know this thing is called a filter. Sometimes we call it as a kernel also. This orange thing as a kernel or a filter also. Now see, imagine what you're doing is that you are, let's say this image was not made up of 0 and 1 only, but it was made up of 0 to 255. Now what would be happening is that the larger values, the values that are two. So imagine there are two numbers in front of you. One is called, let's say, 5, and another one is 230. Now, if you multiply both the numbers with, let's say, 10, which one will become more larger? There are two numbers, 5 and another one is 230. 230 is the person you who are standing. This is your body pixel, right? But the white background will contain values from 0 to like 10 only, right? Because this is the white wall, a pure white wall. So let's say even if we say that there are some tints and something, so the color density will be, or color pixel, let's say it's 5. And let's say you're multiplying the same with 10. So your 5 into 10 will be 50, but your 230 when multiplied by 10 will be 230, 2300. So what is going to happen is that we are going to do a matrix multiplication and then sum up all the things, and these are gathered here, right? All the things are gathered here in this area. Now you might say that what has happened if you have gathered larger values, and then there might be some lower values also, because if you are running this thing on a white border also, let's say if everything is 5 multiplied by 10, everything is 50, right? Doesn't make sense. 50 ko you add up all, it will become the same value, right? Now I'll tell you how things change here. When you run this, let's say this was your original image, this deer was your original image. If I zoom in a little bit to show you, this was the image. If you see clearly on my screen, this was the, let's say, image, right? And when you do a filter of this identity filter, it will return you something like this. If you return this filter, it will return you something like this. If you return edge filter, this is something like this. If you return -1, -1, -1, this is called blur, sharpen blur, edge blur. Then you have box blur, Gaussian blur. So this will happen if you multiply your image with this filter and you run this filter on your image with stride equal to 1. So your original image from here, this thing, this particular thing, this thing will change to these things depending on which filter, through which filter you are multiplying it. Make sense? Now let's say if you're analyzing this thing, this image, what has happened here is that you can easily see that the animals border are now created or sharpened here, right? You can more easily visualize the borders of the animal, right? Rather than with this original image at here, where the borders were not much, they were not much in the same group. Now you can easily do a spread out with just one convolution, and this is just one. We'll like replicate it like multiple times to get more value out of it. Make sense? Now you understand why we are doing this, running a filter over the image. Now this depends that what are the values that you're using inside your filter. Your filter might do a blur of the image also, and it might do a sharpening of your image also. And this edge detection is the something that we want to do right now, that we are very much interested to know that what is the edge of that animal, so that we can differentiate if it's a cat or a dog, right? And this is the perfect example how things are working for us. Correct? Now, once you have done this filter and you have got a very edgy image, now what you want to do is still on this edgy image, you want to capture the maximum values. So now imagine that what you have done is you have multiplied a larger number with a more larger number, right? So your smaller number will become smaller and the larger number will become more larger. And then also you are saying that you want to have the maximum values only. This step is called as the second step in our CNN network, and this is called max pooling. This is called as max pooling. The first thing was running a filter over your images, right? That you have already run successfully and you got everything out of your image. Next, what you're going to do is you're going to do this thing. Okay, again, sorry, one more thing to show you. Let's see. With different filters, you have different feature maps available to you. Let me zoom in so that you can see it more efficiently. So what we are doing is we are trying to run a filter over this, and through different filters, you can see different images are coming out. Different outputs are coming out, right? Make sense? So what we are going to do is next, what we are okay. Now in this, one more thing I want to tell you is that you should have asked me this question, that in this particular GIF that we are seeing here, we are moving the orange filter with one step only. Like see, one step it's going ahead, right? You might argue this to me that okay, this is also arbitrary, right? We can move it to two steps also. And my answer would be yes. You can move it two steps, you can move it three steps, and if it's a very large image, you can move it like more steps, right? So it depends on the architecture of your image and the architecture of the filter that you are choosing, right? Now, when I say how many steps do you want to move, this is called a strides. What it is called? It is called strides. So in our case, right now, the GIF that you're seeing, the stride is equal to 1. When I say stride is equal to 1, it means that you will be moving your image, the kernel, with one step ahead. From left to right, your kernel will be moving one step. And similarly for going down also. So it's, if you see, if you quietly observe that your kernel is shifting downwards with just one row only. It might have shifted to two rows also, right? But because you have set as strides as 1 comma 1, 1 comma 1 means that you will be shifting column to 1, and to row also you will be shifting 1. So till now what we have done is we have taken some arbitrary metrics called as the kernel metrics, right? Then we took some arbitrary values inside it also, some random values. Then we have taken this thing called strides. We have by default we are giving it at 1 comma 1. It means one row to the left and sorry right, and one to the down, right? So we're cherishing all these things as of now. And then we have got out something that is called convoluted fill feature, right? Now, one thing is for sure that your output is going to shrink from the original image, right? So originally, if you see in your example, your image was around 5 cross 5, and now it has come into just 3 cross 3, right? Let's move to the next stage where we have done this convolution. Now our next step would be to get more more edgy features out of it. So what we're going to do is, after we have got this feature map here on the after once we have got this feature map on the left hand side, what we're trying to do is we'll again find out more maximum numbers out of it. So what I'll do somewhat, let me show you where it is, this thing. So let's say on the left hand side that you're seeing is the convoluted filter. I mean, this is the thing that they have returned you after you have done your feature mapping, right? Or your mapping is done. You ran the filter over your image and this is done. And this is the output that you see on the left hand side. Now again, what you will do is you will say that I will take a 2 by 2 ka square, right? I will take a 2 by 2 ka square and I'll pick up the maximum values that are present inside the image. So what is going to happen is currently your answer is in the shape of 4 cross 4, right? And then 4 cross 4, and let's say that you are making a 2 cross 2 circle, and then you have to find the maximum value. So in the first 2 cross 2 you find 6, in the 7 you have 8, in the third you have 3, and in the fourth you have 4. Make sense? Even this max pooling thing has this size that is called 2, that you can see right now it's 2 cross 2, and it has strides equal to 2. Why? Because you don't want to get the maximum number again and again. So let's say if you're taking this, once you have taken these values, you should move to the next thing, right? So let's say this was the first filter of 2 cross 2, and now you have strides of 2. It means it will shift to 2 rows and 2 columns. So this will be your next row column. Next question will be who's the maximum? You'll say 8. So you can see all the values are transferred from 6, then 8, then 3, and then 4. So see, the max pool thing is nothing but, let's say if we go up again, till here where you just got this new answer from your after you have run your filter over your image, this is called convoluted feature, right? Now this convoluted feature is actually nothing but a edgy photograph of your original photo, right? So it contains more edges, more clear edges, and more things, but they're still not much clear to you, right? So then what do you want to say to the model is that, model, give me more heavier amount of images, give me the maximum number of pixels in a particular area. So you say okay. So what you're going to do is the final thing that you have here right now in the pink, 434 243 234, this thing is called a convoluted feature. Now you'll go down. Now once you have got this image, your second step is to take the image and run again a 2 cross 2 filter over it, right? And then with the strides of 2, it means the next step is not one step but 2 steps, right? So your first square will be 1156, right? This one, right? This one is the first square. How much is your total maximum number in this? 1156 is 6, right? So you give 6 here. Then your second, because it's the stride is 2, so your next square will become somewhat like this, 2478, right? Maximum thing is 8. 8 will come here. You have next thing as 32212, then your 3 is equal to 1. Sorry, 3 is not equal to 1, but 3 comes here, right? Then your fourth square, then this is a fourth square, 1034, which is the maximum value, 4. 4 is shifted here. So let's zoom out of this and then let's try to cover them one by one what we have missed till now. So see, whenever you're running this thing that you're seeing on your screen, this filter, whenever you're running, you will never run a single filter on your image. This is what CNN is. You will run multiple filters with multiple different values, and that thing is known as the depth of the CNN. So whenever you will say that from keras.layers import CNN, right, or conv2d. So actually the name in the Keras library for this particular layer is called conv2d. CONV for convolution, CONV and then 2D. So it means that you are using convolution neural network for 2D images, right? So what you will do is, at that instance, it will ask you that how many filters do you want to run on your image? How many random filters do you want to run? That is called the depth of the filter, right? Now imagine this photo here that you're seeing here this is a image of a boat that is standing somewhere near the deck, and you can see water and some grass. Now what it is that right now you have a depth of 3. It means 3 different filters will run on this image and they will produce 3 different convoluted images. Did I make sense here? Imagine that this thing is called as the depth of the convolution. Now depth of the convolution means that right now till this, before this example, we were running only one convolution, right? We were running only one filter over the image and we were getting only one output of that image, right? Now what the model is saying that we will not run one, but we will run multiple. So in this example that you're seeing in front of your images, right, in your screens right now, where this you have a boat inside, where you have a boat near the surface of the earth, you are running 3 different filters, and for running 3 different filters you will get 3 different convoluted features, right? So you cannot control the value that what is going inside the, what is the value of those filters. But yes, you have to definitely tell the model that I want to take these many number of filters, because this will increase the depth of your model, right? So you will say, let's say I want to take 25 different depth of the model, or I want to take 1,000 depth, for the first image. I want to have 1,000 different convolution filters, because eventually their size is decreasing. If you see closely, if you remember the GIF, the height and width of the image is going to decrease, right? But the depth is going to increase. So earlier, let's say if the image was of 1D, sorry, of with one channel, now it is going to convert it into three channel image, because you have run three filters on it. Let's say you ran 500 filters. So for one image, you will have 500 different outputs, right? So see, why we are increasing the depth is because, see, ultimately the model needs to get some or the other final decision thing. See, ultimately the decision is taken by the last layer, right? And you remember that you have to ultimately mold your model to take to the dense layer. And you remember the dense layer are nothing but a single column rows, right? So when I say dense 1024, it means that this is a one column, but 1024 different 1024 different rows are there standing. So you can imagine 1024 blocks one over the above, right? So you have to somehow converge your model to have, so you're converging your 2D image, which has height and depth, and you want to convert it into a depth only thing, right? So let's say that your image was somewhat here like 50 cross 50 image. So what you're eventually doing is, whenever you run a convolution filter, you're reducing its size to, let's say, 35 cross 35. But when that image is converted into 35 cross 35, you're increasing the depth of it, because you're not running single convolution filter, because you're running, let's say, 10. So if the original size was 50 cross 50, now it was converted into 35 into 35 into 10, right? When you will run more, it will convert it into, let's say, 15 into 15 into 100, right? And then eventually you will be having only 1 cross 1 cross 100. Rather than running one convolution filter and having only one answer to the model, what we are doing is we are running 10 and hundreds of filters, so that eventually we are like, in the end, we are clubbing them all, so that we can. So if you have done ML, you must have heard of this thing called ensembling of all the models, right? So let's say that you don't want to trust only one model, but you build three different models, and then you club all these models. This is what is happening here also. We are not running only one filter, but we are running 100 different filters, and then at the end we are clubbing all their results, right? Let me just scroll it up. So when I say filter or feature, I mean this thing, this small yellow thing that is not known to us. This is the random matrix that we know. Okay, now coming back to the problem where we were, that if you are doing, let's say you have done you have just ran a filter over your image, and your image is converted from this simple image to this more enhanced edgy image, right? Now if you go more thing out, so first thing that you were doing was that was called depth. Now what is depth? Depth means just that if you are running different types of convolution filters on our images, then you'll get different results, right? So if I'm saying I'm running a depth of 64, I mean I have 64 different features which I ran over my image, and they gave me the output, right? Second thing is strides. Yes, strides, we already know strides is what? Strides is the step size. That how many jumps do you want your filter to move? So in the GIF, we were seeing that our model was shifting with one space, right? One space to the right, it was shifting. So that time it was stride equal to 1, but if you do stride 2, it means it is going to jump. It is going to take 2 steps, right? Oh, then we have one of the important thing that is called padding. Now you might, if we go up again, if not, let's not go up again, but if you see this thing right here, okay, this is the dynamic one, this is it, right? Let's say if you are here, and let's say that this is the first step, right? It has completed. Now let's say that you have a stride of 2. Where will be the next stride position will be? Stride position will be almost somewhat here. This and this, right? Now let's take an example that you again have a 5 cross 5 image, 3 cross 3 filter, but you have a stride of 3 cross 3. What will happen right now? First is here. I can draw it for you. First will be this. The third one will be, the second one will be here. But at this particular instance, you have only 2 columns. Where is this third column? Right? So what you do is you fill it with zeros here. This is called zero padding. When you don't have enough number of columns to fill your things, what you do? You fill it with zeros, zeros, so that now you can have a 3 cross 3 padding.
Just a quick info, guys. Test your knowledge of computer vision by answering this question. A string of 8 zeros and ones is called what? A. Megabyte, B. Byte, C. Kilobyte, D. Gigabyte. Comment your answer in the comment section below. Subscribe to Intellipaat to know the right answer. Now, let's continue with the session.
Similarly, if you go down, you will have this problem here also. You won't have an extra row. So what you will do is again you will go this, you'll fill 0 in this, 0, 0 and 0. This thing is called padding. What is called? This is called zero padding, right? Let's move to the next thing. This is called zero padding, right? Now once you have done all this, you have run the feature with multiple depth and you have some padding or you have some strides, right? Then you'll get some output out of it, right? Similarly, like you got something here like 4 3 4 2 4 3 and 2 3 4, right? This pink answer you'll get, right? You'll get an image. Now if I say that please run it through a ReLU. Now if you remember ReLU, what was ReLU? ReLU used to give you the answer as it is if the number is greater than 0, right? But if the number is less than 0, it will convert everything to 0. So what we are trying to say is that if there is a positive number, let it go and fly. We don't care. But if something is negative, we are going to convert it to 0. So what will happen is if you give a image, see if this was your, if you can see clearly, let me zoom in. If you clearly see from here, you can see it right now. If you clearly see from here on the left hand side, this was the output from the feature, one of the output from the feature, and then you ran this ReLU thing. This is what has happened. Only non-negative values are there, all the negative values are gone. You can read there also, it was written black is equal to negative, white is equal to positive values. So all the whites are there, blacks are all gone, right? Now once you have done the you have done the ReLU, then you have this thing called pooling that we were just talking about. Pooling is nothing but it is used for reducing the dimensions but retaining the most important features. And this is what we were talking about, that the pooling can be of different types: max, average and sum. Read it here, these 3 lines. This is one of the best, right? And especially for new people who just started learning about deep learning, this is one of the best because it is not using any kind of a jargon word. Otherwise people they use like non-spatial locational background of the image will not, and then you won't have any idea what is going on, right? So what is happening is this is a 4 cross 4 image. You take a 2 cross 2 matrix over it. You do a max pooling. 6 is maximum, take 6. 8 is maximum, take 8. Here maximum is 3. Here maximum is 4. Take all these. So what you've done is you take your original picture. Original picture, you do some feature of you ran some filter. You got the convoluted filter. Then you ran some ReLU, and then on the ReLU you ran a max pooling. So eventually what will happen, let's see if you ran the image on a max pooling. This is what will happen. But if you will see this thing for a very large image, right, you will understand these things also. Let's say if you have an image of 1000 cross 1000 and then you're running this thing, you will definitely capture these things, that what it is doing is ultimately all these buildings are now reduced to a very lower level, has been now reduced to this small image, right? And now if this would have been a high quality image, you could have easily seen that all these tall buildings are now reduced to a smaller level in the things, and we are reducing the dimensionality. Right? This is all what we do in convolution. At the end, we get this convolution and we get somewhat architecture like this. This extreme left was your original image, right? Then you ran some filters on it. Let's say you ran 3 filters. So the size is 3 filters are here. Now out of one image, you can get 3 images, right? 3 different outputs for 3 different filters. Now on these filters, you ran a pooling. Now pooling say you reduce the size of your image, right? Again on this answer that you got from the pooling, you ran a convolution. Again a convolution. Now let's say you already had 3 images. Now you ran 3 again. So 3 for each image will give you 9 images, right? So you'll have 9 images. Then again you ran a max pool. Then again you'll do pooling. So eventually what will happen is your image size, if it was 50 cross 50, this will end up to let's say 7 cross 7 or let's say 1 cross 1. But its depth will increase. Its depth will increase to a very large level. And this will ultimately convert it into a dense neural network. And this is what our idea is also. Make sense? Let's import the first thing first. Import Keras, our best friend. Then we have NumPy, a second best friend, as env. Import matplotlib.pyplot as plt. Okay, let's go to keras.preprocessing.image, and then we have image data generator. Then you have from keras. Okay, let's do the layer 1 and afterwards. And let's make the data generator. Data generator is okay. Image data generator, what does it takes? It takes multiple things. How many things do you want to give? Let's say rotation range. Rotation range should be what, 40. I'm sorry, I have to see this thing with shift range. How much? 0.2. Then we have height shift 0.2. Right, we can what else do we have? Height, width, and then okay, we can do a flip also. Okay, horizontal flip equal to true. Let me move this GTM a little bit here. Okay, then we have zoom also, zoom range. Let's do this as of now only. So our data generator is ready. Data gen is ready. You can see all the things by going here. It can tell you whatever things you have taken, it will do. Now when you are using image data generator, you can do the same with just one thing. You just say rescale. So now what will happen? All your images will be through your will be multiplied through divided by 255, right? Again, your data generator is activated. See, data generator, by saying it's a generator, so it will not give you all the values at once. It will give you the results in batches. Where we read this, that generates batches of tensor images data with real-time augmentation. The data will be looped over in batches, right? Next we are going to do is that we have made this generator here. Now what we can do is we can directly start with our modeling part, right? From Keras.model import sequential, right? From Keras.layers import conv2d. Today we are going to do conv2d, then max pool 2d, then we will use flatten, Then you will use dense. What else should we use? That's it, right? And from Keras dot activation, let's import activations. What kind of activation do we need? Relu and softmax. Softmax, right? Then Keras dot losses. Maybe we'll use categorical cross entropy, right? And from Keras dot optimizer, import SGD and RMS prop. RMS prop. Okay, let's activate all these things. I think we are almost done. We have taken layers, we have taken activations, then we have taken losses, optimizers, nothing else, right? Let's make the model. And before we make the model, let me shift this, drag this here, and close this thing out. We get more space. Right. Now let's make the model. Model is equal to sequential type of a model. Right. Sequential type of model. Now let's pay a little bit attention that how do we make a model out here, right? Let me give some space and then okay. First of all, what I'll do is I will add a conv layer. I am not going to convert this image into a 1D image by doing a flattening. This time I am going to give the image as con2D as it is. That when we were running the convolution in practical, we had this 2D image. We were not doing it at flattening. We were not doing it row major or column major flattening, right? We took the image as it is, right? So you are going to take this image model.add convolution 2D. We're not going to do the flattening part. Now let's see that what does this conv2D takes place. Now con2D first takes place filters. Okay, let's see what filters is. Then we have kernel size. Then we have strides. If you don't give strides, strides are by default 1 cross 1. Then you have padding. Then you have data format. Then you have dilation. Now after that, all these are like default values. They already have some values. The only two things that it expects from you is one is the filters and another one is the kernel size. Now filters is nothing but it's the number of different types of filters that you want, random filters that you want to run on your image, right? And second is the kernel size. Now when you're making this filter, what should be the size of the particular filter that you're going to run on the image, right? You will be telling the conv2D Keras that these are the number of filters that I will use. Let's say I use 64 filters and this should be the size. Let's see more deeper into this. See, now one more important thing, when you're using this layer as the first layer in the model, provide the keyword input shape. So you have to make sure that you're providing the input shape, right? And your input shape is equal to 28, 28, 28. 3 means that for 28, 28, 28 RGB pictures, right? And you have to make sure that your data format is equal to channel equal to last. It means that whenever you're specifying your dimension as 28 cross 28 cross 3, here 3 means that these are the number of channels. But if you are giving 3, 28, 28, make sure that you change your data format as channel first. So this used to happen a lot when there was this framework called Theano. So Theano had this own format of having the channel first. Then TensorFlow came in, it said, no, I want the channel at the last. So there was this conflict a lot. So now you have to specify, because Keras used to support both TensorFlow and Theano backend. So it has this thing called data format where you can specify that you will be providing your channel first or channel last, right? But Theano ended in 2017. So 2017, yes. So you don't have to worry much about data format. Data format should be channel last only. Filters. Now this filter, you are expected to enter a integer here. Now integer, it means that the dimensionality of the outer space, that is the number of the output filter in the convolution. It means, let's say if you give it numbers 32, it means there are 32 different filters, random filters that will run on the image and they will produce the convoluted image. Second is the kernel size, an integer or tuple list of integer 2 specifying the height and width of the 2D convoluted window. Strides can be integer or tuple, same as above. If you don't specify, by default it is 1 cross 1, right? Then you have padding. Padding is either valid or same, right? The it is saying that same is slightly inconsistent across backends with stride is equal to 1 as described here. So you should always take it as a valid one. works better. Then you have data format. These are all like numbers that are already predefined. You don't have to look much about it. But let's start with the convolution 2D that we have to make, right?
Just a quick info, guys. Intellipaat provides artificial intelligence online training mentored by industry experts, the course link of which is given in the description below. Now, let's continue with the session.
Let's say that we want 32 images of 3 cross 3, right? Next, you have to give it as a input shape. Input shape, let's say that we are going to give 150 cross 150 cross 3. We have still not decided how our shapes of the input will look like, but we have decided that we'll go with 150 cross 150 cross 3. Now, once you have specified this convolution, you have to specify a activation function also, right? Either you can specify here only in this con thing, you can just go and say activation is equal to, or you can specify by again saying here model dot add, and then you can have a activation is equal to. Okay, we have not gone here from. Okay, so you can add an activation layer here also. I generally don't like this. I just add it here only. Activation. We love relu. We'll go with relu only. Relu is the most important thing. Okay, now after convolution and then doing an activation, what was the next step that we used to do? We used to have a max pool. Max pool again, let's go. Max pool, what was max pool doing? Max pool was doing nothing, but it was bifurcating your image into parts that you specify and then picking up the maximum value out of it, right? So it's saying that your image, let's say the pool size is 2 cross 2, it means that the image will start from the kernel size of 2 cross 2, and then out of the 4 values it is going to take the one which is the maximum number, right? But let's say we want to change this. How to change this? You say pool size is equal to, let's say we take it 2 cross 2 only. Now this thing that we have written till these these 2 lines which contain 3 specific operations, this thing is called as the chunk. Single chunk of convolution. These 3 steps. Which one is the one? One is conv, then you have activation, and then you have pooling. These 3 things together are called as the chunk of. Now what you can do is you can just copy paste these things and then you can have more chunks. But this time you have to make sure that you're not using this input size, because input size should always be inside your first thing only. I'll increase this number to 64 here, or let's keep it 32 only. Again, I will copy this thing. Let's make 3 chunks because our data is not that much complex. Let's have 32, 34, 64, and then come here, and then you have model.compile. Right, compile me. You have loss is equal to categorical cross entropy. Let's find it in double quotes. Then you have optimizers. Let's use SGD only. This is the one that converges the fastest. Then you have matrix. Let's use accuracy. Right. And then we'll do model.fit. But as of now, we don't have any input outputs. Let's just make the model sit here only. Right. Nothing much to do. So what we did actually here is we just made 3 convolution filters. One is this 32. When we started this off, 32. We said 32 numbers of different so imagine this one image will now become 32 images, but the size will drop due to max pooling, right? Again, these 32 images will now become into 32, but their size will decrease. Again, the height width will decrease. Now these 62 will become almost like what will they become? They'll become 64. So they become more, and their height width will again decrease a lot. One thing that I forgot to tell you is that this is not the end, right? Our end will be somewhere when the output will be only 2 units, right? This is not the output, right? We have to do a flatten here. Remember? Because ultimately, see, our answer will be in 2 words, right? Either 0 or 1 in 2 letters, right? So the output layer will only have 2 neurons, correct? Model.add, once is flattening. We have done the flattening, then we might use a dense layer. dense layer में let's say we take 1024, then let's add activation. Let me add it here only in this thing. Activation is equal to relu. Then let's decrease this by let's say 512. Again have activation of relu, and then in the end let's have the final well will have how many? Only 2, dense and 2, and this time the activation will be softmax, right? So this will almost become like this. So our model should almost look like this. Just a second. Does this look like the same? So first convolution, then pooling, then second convolution, then pooling, then imagine we have a third convolution also, then we have a fully connected dense layer, and then we are reducing the number of dense layers from 1024, then 5112, and then immediately 2. So this example has more, but this is somewhat like what we have an inspiration code, right? Data generator. Now what we have to do is that we have to make a train generator. Train gen is equal to data gen dot flow from directory, right? Flow from directory, where is our data? Our data is just behind this. Then we have cat dog cat. Yes, dog cat small. We have more generator small. The format of this folder should bear. Let me show you. You all know how the folder looks like, right? LDIR is equal to, if I show you what is inside data generator small, then this is nothing but the two folders, category wise folders, right? These are category wise folders. Okay, so let's move back here again. So we have our data generator here already. We will say that please go to this directory data generator small and then flow these images from this directory, right? I am also telling it that you should have a target size of 150. So whatever the size of the image is, resize that image. Say if your image was 1056 cross something something something, this is not getting cropped. This is resizing the image, right? So you are saying that you want to convert your image into this, then you have to give the batch size at how many images that you want to read, right? Let's say I want to read 32 images per batch. Now you remember we have 400 images for all the classes, for all the two classes. Now I am saying 32 batch size. 32 batch size means that if I divide 400 with 32, it will give me around 12, 12.5, or let's say 13. So this is always ceiling. So this will always be a 13 buckets we will have. So our epoch will show a count from 0 to 13, right? Batch size 32, and then we have, then what do we have? We have data generator, then we have color mode, it's already RGB, then we have classes is equal to none. We need to keep it none. Then class mode is categorical. Yes, we want it categorical only. We have batch size of 32, it's by default. Shuffle equal to true. Yes, seed equal to none. We don't want seeding. We save directory. No, we don't want to save. Nothing. We don't want to save. We want to just start the thing. It says that it found 401 images belonging to two classes, and that was correct. We had only two classes. Right, after we have got our train gen ready, we should use the model dot fit, right? So fit will not work here. We will use fit transform. Model dot fit generator, sorry, not transform, generator. Model.fit generator, you have to give it what? A train gen that you have just made. Next, you have a step per epoch. Step per epoch is none by default, but this is what you think, right? Steps per epoch is what? That how many buckets will come here. So you get the idea, right? What was the number that we just calculated? That was 13. I'll tell you again how it came 13. So you have 401 images in total, right? And you are saying that you will have a batch size of 32. Batch size of 32 means that in each bucket you will have 32 images. Then how many buckets will you have? 12.53. Now bucket can be an integer only. So what you will do is you will do np.ceiling. It means you want the upper bound. Upper bound will be what? 13. So you will have 13 things. Or what you can do is, that is the most brilliant thing that all you always do is +1. That gives you the idea, right? So what we are going to do is we can write here that steps per epoch will be, so one epoch is what? When all your images are gone from the model forward and backward once. That is one epoch. Now you have 400 images. You are only taking 32 once at a time. So your model will be taking 13 times each bucket of 32 images, and then it will cover 400. So your steps per epoch will be what? 32. Then you have epochs. Let's say 10 epochs only right now. I don't have much RAM in this, but okay. And then you can say verbose equal to 1. Verbose equal to 1 means that you want the output to be printed. Yes, we want. You can have 0 or 1 dependingly. And they have 2 also, if I remember. Yes, verbose is equal to 0, 1, 2. 0 is like totally silent. You don't want anything. 1 is with the progress bar, and 2 is with the one line per epoch. Right. Okay. Then you have these things called what is this? Class callbacks. Right? How, when you are running a very large model, how do you see the losses and the accuracy of this? Right. Similarly, you can have validation data. If you have validation data, you give your validation data where it is. Right. Validation steps. How many steps do you want? And then you can further give this thing. We don't have much. We will say we will remove this thing. We will run this again, and again. And our model is started, and my CPU has started heating up. Okay, let me stop it here. I forgot to do one thing here, that you have to take this thing in some output history. Now we will start this. See, I told you this number is going to be 13, right? So we are saying that we want 10 epochs. That is a different story. But in each epoch, how many times it is going to run? 13 times. 13 times forward, backward, forward, backward, forward, backward, 13 times. And each forward, backward is taking how many images? 32 images. Now you can see your model is giving 54% accuracy. Losses are decreasing 0.69. Oh, 70 increased. 69 decreasing again. Okay, this was a very bad line. The accuracy decreased. Okay, the model is recovering slowly, slowly, slowly. Oh yes, increasing. Just 2 more steps and our modeling will be done. This is how we do. Now let me check one thing, because I think I did something. Because this is not what the accuracy I was expecting. The accuracy should be like, okay, so we have a data set also small one. If I give it the big one, let's try it. Then it should work better. Okay, let me run this again. Let me restart the kernel only. Epochs are also less, so you might try to increase the epochs also. And I might need to do one more thing. I might need to increase the batch size.
Just a quick info, guys. Test your knowledge of computer vision by answering this question. Computers process data into information by working exclusively with which of the following? A. Multimedia. B. Words. C. Characters. D. Numbers. Comment your answer in the comment section below. Subscribe to Intellipaat to know the right answer. Now, let's continue with the session.
How is the batch size uh, affecting the model? One is that, okay, it is using the RAM, right? Because 128 images are now going inside the model. But what else it is doing? So let's say I give you this example. Let's say that there are two animals that are not known to you, right? I am giving you the images that this one is animal A and this one is animal B, right? Now, if I show you only one image at a time and then I ask you that tell me who this thing is. Or another case is when I'm giving you 100 images and then I'm saying 50 are this, 50 are this. And then you see all those, okay, 50 animal A, 50 animal B. And then in which state you will be able to give, when I give you next image, in which state you will be you can give me better answer. Because I want to show you one more thing here is that we have two classes right now, right? We could have done one more thing. We could have asked it here that we have, no, not here. We could have come here and say that this is only one. And rather than saying that this is cross entropy, we could have said Keras dot losses dot binary cross entropy, right? How I'm showing you that what is the difference between categorical and binomial. So what I'm saying is why I took one only, because now my answer will be in 0 and 1. And why 0 and 1? Because if it's not a cat, it is a dog actually, right? So it's actually, it's so how I've converted two categorical problem into a binary problem. Binary problem is what? 0 or 1, right? Let's say one is dog, then 0 will eventually become not dog, and not dog in our case is cat. And this is one thing that you should always understand. Let's say that if your model is trying to predict three things, one is cat, dog, and elephant, let's say. And let's say you give a image of giraffe here, right? You have trained your model on cat, dog, and elephant. And now you're giving it an image of giraffe. What will it predict? 0, 0, 0. Okay, one answer is 0, 0, 0. That it will say 0 for each probability, right? So one thing that you should always remember is that the sum of the probability for the three classes will be equal to 1. At the softmax, we always use a softmax in the last layer. And what is the responsibility of softmax? That it will give you the how many probabilities? It will give you the probabilities that much classes that you have. So if you have three classes, it will give you three probabilities. And the sum of all the probabilities will be equal to 1. So 0, 0, 0 might, I mean, it will not be the answer. The answer will be that the model will say that, see, I know that the answer is not right, but because I'm not trained on this, and the elephant is not matching, it's not matching even to your dog, not cat. But softmax, what it will try to do, even if it is giving very less accuracy for each, it will, based on the percentile, it will give you the probability which will sum up to 1. That it might not give high probability for cat and dog, but it might give some probability for elephant and dog also. And it might not cross 60 or above for any one of the category. So it might be like 30, 20 for cat, 30 for dog, and 30 for elephant. I mean the sum will be 1. It will try to do somewhat like this. So always remember, your model will always predict from only what you are trying to tell it, right? I will like to start with callbacks because I have this sheet on 6 Jan where we did this history thing out here. History thing, we did all this plotting and all. So I think we should go with callbacks. Okay, so a callback is actually a function that you can execute after every epoch is run. So let's say that your line is somewhat here, epoch here, and then you come here. Your accuracy, final accuracy is printed, your validation accuracy is printed, and then whatever you want to do, you can do at this stage is called a callback. Again, this will be executed when your second epoch is completed with all the 4 batches. Then again at the third end after this, and similarly. After each iteration of an epoch, if you want to run something, you get this thing inside your callbacks. Now, how do you get callbacks? Very easy. You just say from keras.callbacks import callback. See, callbacks is nothing but callback is that, let's say that after every epoch, once a epoch is run, and if you want to perform some operation after every epoch, you can call that function inside a callback. That's simple. So there are multiple things that you want to do after every epoch. Let's say you want to store the results, or let's say you're writing your own custom laws, or let's say you are writing your own custom let's say optimizer, right? Or let's say you are decreasing your learning rate based on some particular parameters. So then you can write, I can show you, I wrote this code somewhat long time ago, and this contains a very good callback thing. Let me show you. So if I show you here callbacks, here I'm using model checkpoint and learning rate scheduler, right? So I'm using two things. One is called tensor, one is called model checkpointing, another one is called learning rate scheduler. Now what this model checkpointing is doing, this model checkpointing is saving the weights after every epoch. So what it is it that after every epoch, if you want to run any kind of a function, any kind of a method, then you can specify them here in the callbacks, then they will be executed and they will be recorded in the tf.event files. Again, after the second epoch is completed, you run the callback. After third, you run the callback. After fourth, you run the callback function. So we were here at this thing that, let's say that you define your own custom step decay function. After you have done with the step decay, how do you call it? You make it your loss history, and when you are doing a dot fit, you call your callback here, right? So we'll do the same thing out here. What we'll do, we have this thing called tensor board. So if you see, I have imported this thing called, this one is not needed. From keras.callbacks import tensor board. So what I've taken is tensor board is, I'll show you what tensor board is, but let's first implement it at what tensor board is. Before you are doing your training, you have to do a tensor board is equal to tensor board. If it is in capital, it's a class where you have to instantiate. You have, let's say, log dir is equal to, let's say here only, or let's say that you want to make it as a logs. Okay, So what it will do, it will create a folder called logs in my current directory, and then it will store all the information there, right? What it will do, it will store all the information there only. And let's say I don't want to go in the logs folder. I just want to stay in my dot folder only. Stay wherever my Jupyter notebook is, just create the file there only, right? But you can specify wherever you want to go. Now, once you have done this, this will start this thing, TensorBoard. And then while you are in your fit generator, you will call the callbacks. Let it complete callbacks. And then it will be a list. List me, you give your TB, right? And let me increase this to 15 for now, right? And let's start the model.fit again. Now, while we are doing this thing, what will happen is, let me show you. If you go in the files, you see here, there is this thing that has started building up, tf.event files. After this first epoch, you will see a new file here, last modified. Okay, now you will see it up here after first epoch. Okay, yes, you can see here. If I do a last modified above, okay, it's not coming. Then you have to go down and let me show you. See if you can read this thing called here on the downside. I'm just marking it with the blue marker. This is called events.out.tf event file. So what it is generating is the TensorFlow is generating its event file, and they are stored here. Now, how can you open a TensorBoard? Very simple. Open up your console. You go there in the console. Click on the console. Okay, this is Windows. This will take a little bit time. Enter, and you have to just say TensorBoard. TensorBoard is by default installed when you are installing TensorFlow also. So TensorBoard TensorBoard hyphen log dir is equal to, or I can show you the help first. Sorry, board hyphen help. Okay, this is not good. This is start this thing. Okay. Okay, let me run it in a simple environment. Just a second. This is your Intellipaat working directory. We are in notebook 3. We are opening the CMD. Let me open it up. So see what I ran, I just simply said TensorBoard, and this will start the TensorBoard inside that directory, right? Now once, okay, I did a mess. I should have specified this thing, but okay. First thing first, I should show you the help hyphen help, that what are the different parameters that you can give. There's one parameter that is called log dir that you have to definitely give, that where your logs are kept, right? Where your logs are kept inside which directory. Okay, this is taking a small time. So now they have changed it to helpful. It's not help. Okay, so these are the different flags that you can give. You can give a tag if you're running multiple. You can give port number, which port do you want to run. But the most important one is this hyphen log dir. This one is the one that is the most important that you have to give. There are multiple things that you can do with TensorBoard, but the most important is when you open TensorBoard and where you are. So I'm saying dot means wherever you are present, the log files are present there only. Let's go to our browser again, and in the browser, let's open up our localhost 6006. That is the by default port that we have. Takes time to run this thing. Let me check. Okay, so it runs on this thing. So here what you can see is the beautiful TensorBoard. It's loading. Does multiple tabs, and let's, if we see, our model is running on the 11th epoch. So you will have all the information till 10th epoch in this thing. So you can see the dashboard is here, and these are the loss and the accuracy function. These are the same numbers that you have here. So you have something that is greater than 7.1.0. And if we go back to our model and if we see what is the accuracy on the first epoch, that is 50.3. Sorry, this is the loss, 71.6. Sorry, it's correct. It's correct. So it's showing you the accuracy on the top and losses at the below. So your loss was greater than 7.10. If you go on the mouse, if you put it somewhere, it will show you each and everything, right? You can smoothen it up more to see the exact accuracy number. If you're running larger numbers and you want to smoothen it up, then you can smoothen it up with here, right? And this is for loss. Whatever different kind of if you would have validation accuracy or validation lot, they would have also been plotted here. These are the two things that you can definitely see here. So you don't have to actually view this thing here. So what you can do is that you can quickly come up here and you can say, okay, my step number 6 is the best. This is performing the best. I will take its weight, right? Same here also for the 6th step, you had the lowest loss and the highest accuracy. So you'll say, I'll take this one, right? Now the most important thing is visualizing your model. So if you click on this graph button, you will see your model here, how it looks like. This is how your model is actually. So if you can zoom in, you can zoom in and see how these things are. First you had this convolution one, right? Then you had a max pooling, then con, then max pooling, then con, then max pooling. Then you had a flattened layer, then you had a dense layer, then again a dense layer, and then you had a matrix to identify what kind of a matrix what kind of accuracy it is, and then you had the loss here. If you click on this loss here, you will be taken to the loss section. On the right, you can see that this is giving you all the things out here. You can also shift your model here, and then you can see this is how your zoomed in variable are. Sorry. So if you click on each thing, then you can have this. Let's say I click on this dense layer, then you have this thing on dense sub node 13th node. This is the 13th node. The input is coming from dense 4. That is absolutely right because dense 4 is there, and then you have dense 5. And then the output is going in dense 6 for the matrix multiplication with 512 variables. And that is absolutely right because in the first we had 1024, then we had 512. And then the output will be in the form of 7 tensors. Absolutely correct. If you go this thing and if you just do a model.history, it will model.summary, it will be the same. Right? These dimensions are the same that you see here. Then you have control dependencies. If you want to have more information on the graph, then you should definitely show this to client. These are like showing here. You can go anytime, you can go there. It has multiple things. You can even see images inside it. So right now we are not given, but if you would have given, you can see your things out there also. I'm so sorry. Go back. Graph. You have multiple things in here. You can download this graph also by clicking on this fit to screen, and then you could have download this also. Session, you can see multiple devices also. Let's say I have only one device. You could have multiple devices, and then also you could have taken trace inputs. So you want to see where your inputs are going till now. Let's say if I click on this, it will show me how is my input working for this particular section, right? Choose legends, whatever you want to have, right? It's a very useful thing. You will come to know more about this when you're training, very large layered networks. In our relative number means what is the difference between the previous and the past one. So it's like a step function that you're doing. Then you have the step is the exact one that the recording for each epoch, and relative is that you're trying to get the number from the previous one, how it is changing from the previous one. But the only thing extra that you have to do, two things that extra that you have to do to bring TensorBoard was that first of all that you have to tell the model that model please after every epoch you have to save this things for me inside this file called callbacks. Callbacks ko you have given a list me you have given tb is actually what, it's an instance of TensorBoard. And TensorBoard, how did you declare it? You declared it from keras.callbacks.tensorboard. Now once you are done with this TensorBoard, how did you open the TensorBoard? Tensor board you opened in the command prompt, you went to the folder where you are running this thing, and then you just write tensor board hyphen log dir. Transfer learning. Now, what is this transfer learning and how does it matter to me and how does it matter to the world? Now, if you are working in computer vision, you should have heard this name like multiple times, not from me, but from the world also. Andre Kerpati. So he just said one thing, don't try to be a hero. Now, what does it mean? Means that let's say that you are working for a client problem which has very less data. Now, one thing is that you can learn everything from scratch for the model. So there he says that do not try to be a hero. If there are things already made for you, do not try to reinvent the wheel. This is what the concept of transfer learning is. Now, transfer learning says that let's say that you have something already pre-built, something has learned all the features already. And why are you trying to learn this? So every year there is this competition that is called as the imagenet competition. You might have heard of this multiple times. So what this ImageNet is, I would definitely encourage you all to also access this thing. This ImageNet, I can give you the URL in the chat. This is actually a data set of 1 million images in 1000 categories. Now they have increased the images. They are of more than like, oh, here they say they have 14 million images and 21,841 synsets. Means these are the different categories. Now the data set that you are seeing is of 2011. Here you can click on any of the particular category and it will take you subcategories and then sub more categories. So you can see if I click on animals, I have these ranges: creepy, crawling. So they are like multiples, like games, animal games. You have game birds. So there are multiple subcategories also. You can view these things. So you can imagine what kind of a diverse data set it is, right? From ranging from animals to fungus, natural objects, plants, geographical formations, larva. You have images for larva also. So you can have a very diverse category inside this. Earlier it used to have, so you can see even for like when I clicked on this thing called, this is actually larva. Larva maybe you have 1, 2, 3, 4 images. You can further go inside this thing larva also. Then you can have like tadpoles. Let's click on tadpoles. Tadpoles may you have 1153 images. So it's like a moving inside thing. When I click on tadpoles means you have like 0 subcategories inside this. So the number 0 here, it means that how many subcategories does it contain, or is it the last child? So tadpole is the last child, it has no subcategory. But if you go for caterpillar, it has 29 more subcategories inside it. And canner worm has another more 2 categories. My internet sucks, otherwise it would have opened. You can go for the tree view. Okay, if I click on larva here, you can have the tree view of this whole thing. You can download them also, but this is like a download is only available if you like one by one image. It's not available like a bulk image of all the things. To download the data set for ImageNet, you have to be from some academia and you have to provide them some proofs. Then they give you the download link for that also. You can download the things from here. Now every year they have this things out here, and there are like major competitions being held on this, that if you can train your model. Now when these models are trained on data like this, now just imagine how diverse the data sets become, right? They learn multiple things, not only just cat and dog features like how it is or how is that, but buildings, aeroplanes, vehicles, mobiles, microwaves. So they're learning almost everything. So they are learning edges and functions for everything. Now in this paper, now they are telling that what are the things that they are learning inside this thing. So they are telling that this slight yellow part is actually the convolution. The green one is the max pool. So you can see there are three convolutions, then a max pool, two convolution, then a max pool. Then they have a ring of convolution. Blues are average pool. So this is how they describe their model, right? And if you go there, they have provided the weights also for this. So when this orange filter, whenever this orange filter is moving, we didn't knew the values of this orange filter, right? We randomly took the values of this kernel feature, right? So when you were making your own this convolution, and you said that you want to have a size of 3 cross 3, and you want to have 32 different kinds of these small yellow these yellow metrics. Now what was the value that was initially taken? It was random values, right? But when your model started training itself forward, backward, to minimize the error, it certainly came to a point where it has optimized the value of this orange filter that is moving, right? and these are the optimized value that are saved and called as the weights of the model. And you know what, every time we do this thing, every time we do this thing called model dot summary, it tells you this thing, that at this particular layer you had 896 values that are to be saved. At this particular layer you have 9000 values to be saved. At this particular layer you have 18,000 values, and then you have similarly these values, and then you add up. These are called total trainable parameters. These 19 million parameters are actually saved inside your model.save weight thing. So just imagine deep learning. What it is doing is, let's say this is your input, this is your input image. Let's say that this is a simple operation that you have to multiply it with something called, let's say, alpha, and then your answer will be output, right? So you have to convert your input to output, and then you don't know the value of this alpha. So what you do, you do a deep learning training and you want to calculate the value, you learn the value of alpha. Now you have the value of alpha, you save this value of alpha. Whenever someone gives you the input, you again just simply do a multiplication and then you get the output, right? So this alpha thing is actually these 19,000 parameters. Did I make sense to you? Simply, right? This is what we do in machine learning also and deep learning also. What we're trying to do is, it's a simple equation that you have to do some or the other operation with the input to produce the output. Now I am just simply saying this is a multiplication, but no, it's not multiplication. It's like a very complex thing. But just to simplify this thing, let's say that there is some kind of a relationship, some kind of a function with input. So you have some kind of an input function for I that is giving you the output. Now you have to find this function only. This is your only job, that you have to find that what is this function. Once you have this function, next time whenever you have the input, you just pass it into this function and then you will get the output, right? This is what is called as the weights of the model. Nothing but the optimized value of all these 32 64 convolutions. This was all about weights and all. So these are all the values that are saved in your weights, right? So this is so what they do, they will give you the code also, and then they will give you the weight also. So when they are giving you the weight, it means that they have given you everything. You have now the trained values of those things. Of which things? These things, these convolution that are here, these convolution. Now you don't have to train to get the values, you already have the optimized value for all these convolutions, right? All these convolutions, you have the exact optimized value, so you don't have to train them. When they give you the value, your model is like already filled up with the optimized number. Now, if I say in theoretical terms, what it is happening is, let's say that you have this thing already in your, if I tell you what it is actually, so this was the mathematical thing, right? So what is happening is that your model has, let's say that you just copy pasted this particular model, and then in the end, rather than in the end, so see, if I'm saying that this ResNet was trained for 1000 classes, can anybody tell me what will be the last of the dense layer? This last dense layer will give you how many probabilities? If I say that there are 1000 categories on which this ResNet model is trained, there are 1000 categories on which this model is trained. What will be the number of dense layer at the end? What will be the value of the dense layer at the end? 1000 only, because you want to have probability for each class, right? You want to use this particular model only, but you want to use your cat dog image dataset. Now you cannot have these 1000 layers at the end, right? You need to convert this 1000 to 2. So your 1000 will be here. You have to cross this 1000. You have to cross this 1000 and make it to 2 only, right? So now this is something that is called transfer learning. Now what is happening is that you have this structure already. You have this structure net already made. Let's call this as net, this thing as net, and the weights as the weight. You already know, right? So what we are doing is that we already have a model. We already have a net prepared with us. The only thing that we have to do is that we have to remove this last layer, remove the 1000, and put the 2-layer model there. Correct? And because we have the weights already filled in them, we have all the weights filled in them. So what we will do, we will not run the model, we will not back propagate everything like back and forth, back and forth. What we will do is, we will just run the last layer. We will just run the last layer to be trained, because everything is already trained, right? These layers are already trained. They are like super best layers in their nature. What you are just doing is, you're just removing the 1000 layer, putting a 2 layer and then training this layer. Transfer learning mein what you are doing is, this is your VGG model, right? So it is saying do not touch this green part, let it is as it is, just train your this part, lower part, dense layer part, and then change it from 1000 to 2, right? That's it. Now let's come to the second example, where let's say you have a very similar dataset and you have a large dataset also.
Just a quick info, guys. Intellipaat provides artificial intelligence online training mentored by industry experts, the course link of which is given in the description below. Now, let's continue with the session. Test your knowledge of computer vision by answering this question. A string of 8 zeros and ones is called what? A. Megabyte, B. Byte, C. Kilobyte, D. Gigabyte. Comment your answer in the comment section below. Subscribe to Intellipaat to know the right answer. Now, let's continue with the session.
Then you have to go with fine tune. Fine tune, I'll explain you what this fine tune is. Don't worry. So let's for both the examples, if your dataset is different or similar, you have to use fine tune. Don't worry, I'll tell you fine tune also. But let's jump to the second part that you are asking, right? That you are asking this right now. That let's say the dataset is very different. It is not equal to somewhat like what you have seen. So what you want to get from your older model is, or from the VGG or ResNet, what you want is you just want a generic part, right? And all the generic informations are present on the top layers, on the this top layers, this 64 con, 128 con, or 256 con, right? So what it is saying that you use the transfer learning, but with low level features and classifiers. So what does this mean now? This is saying you that please go here and then freeze the model till here, or at least till here, but train your model below this line. So you are not only remodeling your classifier from 1000 to 2, but you're also training this last layer of convolution also. So these are different kinds of combinations, that where do you want to freeze your model and then where you want to retrain, right? And then whenever you are trying to do this thing, whenever you are trying to, let's say if I remove this thing, and let's say if I say whenever you are trying to train something below this or below this thing is also called as fine tuning. This is the same thing. So if you are doing something that is below this line, this is somewhat like you're just changing the dense layer, and the below something that is flattened, that is called transfer learning. If you are retraining your conv layers here or here, then this is called fine tuning. Nothing much fancy. So what you're trying to say is that you're trying to freeze your model till here. It means that you're not going to run this part. You're going to keep as it is, and then you're going to train this section. Forward, backward, forward, backward, forward, backward, forward, backward, forward, backward. This is input, then you have convolution, then you have your dense layers, and then you have your softmax. Now let's remove this input part, right? Because input will vary for everyone, so let's remove this. But this convolution, let's freeze this part, right? Let's freeze this part. Let's keep it as it is, right? The dense part also, let's keep as it is, right? Now what I'm trying to ask you to change is this softmax layer. And you have weights for all the thing, right? Vanya, you agree with me, right? Because we have weights for everything. Now what I'm trying to say is that please do not load the weights for the last softmax layer, right? And unfreeze this green layer, and other all these in the blue, let them freeze. When I say freeze, I am saying that all the forward and backward propagation is not going to happen there, right? The model is already, your model is already, it is having weights there, and what you're trying to say is that you have freeze the upper layers and you have unfreeze the lower layers, and you will train them only. And this is how you will see. Now did you get the trying what I'm trying to say? The training, all the forward and backward propagation is going to happen till here only. And let's call it as article. This time let's do, and let me show you how to do the magic. import. Now you have multiple things: dense 121, dense 169, dense 121, dense inception, resnet. Depending on the nature of intensity that you want, you can use. I love VG16. This is a very small network, small in weights, because this is just a 16 layer. You can just easily compare that we have done till now. That if you go and see in this, if you go in our class only, this is the VGG, right? This is the VGG, but this one is ResNet. Now imagine the number of things going inside this thing. How many convolutions are there? 1, 2, 3, 4, 5, and there are 100. So ResNet, there are two types of model. One is ResNet 51, and another one is ResNet 101. And I think both are inside. No, ResNet 50 is there only in this. Inception has two. Inception has version 2 and 3 both inside it. They are like literally heavy. And when I say heavy, I mean very heavy. So what you can do is you can call your model. Let's call it model VGG. Model VGG is what? VGG. And then you have to give your that you want to have. Now depending on the thing. Now see. Now depending that you want to do the fine tuning or transfer learning. Depending on that, you have this option called include top. Now what does this include top means? Whether to include the three fully connected layers at the top of the model. What are these three fully connected layers? These are the one that I was talking about. This thing. Do you want these three? This is called the top part of the. So generally people get confused. I was the first person who got confused in this thing also, that this is the top, or this is the top. This convolution is the top, but Keras say this is the top part because this is giving you the output. So they say this as top. So Keras, when it says include top, it means do you want to get these three dense layer output also, right? So let's say that you want to get it or not. Let's say no, we don't want. We will do it our own. We will make our own top three layers, right? Then you have the second thing that is called weights. Now weights, which weights do you want to get? If you see, it is one is called none, that is like randomly initialized, or another one is the imagenet. If you see, I've selected this one. Imagenet is the one that you will that is from the this challenge, imagenet challenge, right? Or if you have your own custom weights also, you can give them here, right? Let's say that we will train the top layer also. So what you can do is you can see here for I in for layer in model VGG dot layers, you can see all the layers here. Print layers. These are all the layers. Layer dot trainable, it will give you true and false. So see, by default these layers are trainable equal to true. The first one is false because this is the input one, and you have all the answers. What you can do is you can simply do control C control V. So input layer you cannot train, but convolution you can train, you can train till last also. But we don't want to train this thing, so we have to say trainable equal to false. Till when? Till this number. Let's say even till this number, right? Depending on your problem, you can set this thing to trainable whatever you want to, right? And then you can have your thing out. So let's say that we keep this till here. We keep this till here, and then we keep everything, and then we say that we don't want to train it till here. So if I get this number should come out to be max pool 2D is the last number. So layer model ggg dot layer, and this number should be 10th number. 10th number is what? 160. No, it's still down. 13. 13 is gone. 14. 160. No. 15. 15 is again gone to 16. What? Dance 9. 19. 19 is above. 18. So till 18, this is the FAD68. You can match this number. FAD68. Till 18, you want to say that we don't want to train you, sir. Right? So what you will do, you will say for I for layer in model VGG till 18. Let's say 19, because you want to get one. Layer dot trainable equal to false, right? Now what we will do, we will again recheck that we have done the good things or bad things. Let's check. Everything is trainable equal to false, 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 false till here. See, false till here. The lower layers we are going to train. Train is equal to true. So now what we can do is we can move our layers, and we have got the layers, we have got them false till here, right? We have got them false till here. They are not trained. We will train this till flatten. Till flatten, what we have done is we have made them as true. Till flatten, we have made them as true. Now what we will do is we will add our own layer, right? We will add our own layer. Let's say from Keras dot layers import flatten. Okay, so what I'm trying to do is I have this flatten, this dense, 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 right? And then we will put another dense here, right? Now what I will do is I will say that what I have got from that output, x is equal to model vgg dot output. Now what will happen, everything that is being till there will be outputted to me, right? And then I will say x is equal to model vgg dot add model vgg. What is happening, this is, let's say, dense. You add dense and add dense to what, x, right? So what is happening, I have given this output to what, x. Then x ko what I am doing, I am giving a dense to x, right? Or what I can do is I can do this, and then I can say type of x is what, dense. Okay, so x is equal to dense. I will say make a dense, but where to attach the dense? Attach it to x only, back again, right? And how many, let's say reduce it to 512, and then again copy this thing, and this time make it to 2 only, correct? And let me copy paste this line in this line only, so that we are not playing with x again and again, because this will hurt the model a lot, right? And if I check now x will be a ops tensor. Cool. What I did was I just added this one more 2 layers after this dense layer. So I know this dense layer was of 1000 categories. Now I have reduced it to 512 and then 2. I had to do one more thing. You guys forgot that here I have to add activation also. Activation. Let me add softmax, and here also softmax. Here I will add relu, right? Now once you have made this thing, you will say from Keras dot model import model. Now what I will do, I will pass this x through model, right? I will say final model is equal to model. Model will take two things. First is the input. Who is giving you the input? So input is from what? Model vgg dot input, right? And who is giving you the output? Output is given by x, correct? What I am trying to say, I am trying to make a final model. This final model has the input from model vgg.input. I mean this layer, right? And then you have output at x. X was what? This dense 2 with softmax, right? I should have, we have done one small error here. I will tell you, if you have got that error, then it's very good. Now see, eventually how many FC layers did you have? You had a final FC layer, then you have a prediction layer, right? Now let's see what you have. You have a flat FC layer, then a FC layer, then a prediction layer, and then you have dense 2 layers. Do you see this? This is how you are connecting your models. Do you get the idea, everybody? Then you have to do nothing. You have to say model.compile. Sorry, final model.compile. Final model.compile. Optimizers is equal to Keras dot losses dot categorical cross entropy. You have Then you have optimizers is equal to Keras dot optimizers dot sgd, right? And then you have matrix is equal to accuracy, right? And then you can run your final 32 images per head, and class mode is categorical. I think it's categorical by default. Yes, class mode is categorical. You don't need to give. This is your generator. It's ready. Generator is ready. Now you have to do nothing. You have to just say to your model what you have to say to your model. That model, final model dot fit generator. And then you have to give train gen epoch. I will give only 2, and then start this thing. This will start your modeling. Quite easy, right? Practical point of view, it's very easy. You don't have to do anything. This will blow my laptop. I will not run it much because it's like 500 MB of weights running in and out, and my laptop is very chotu, taking time. See, it froze. Okay, but this is how you can run. And I think this is the best thing you can run it is in Colab. You should definitely run this thing in Colab. Colab, it will run really fast. It will start. See, you can see even with the first, what do you say, batch only, you have got an accuracy of 53. If you run it for like 20 or 30 epochs, you will get an accuracy of around like 86% in the starting only. So this is the advantage of doing transfer learning. Your model was still it still take time to learn these things, right? But here you can see it's learning. See, 54. This will take 8 minutes to complete one epoch for me, but important point is it is giving me the accuracy, right? Okay, stopped. Let us do. Okay, so model VGG dot output. If you print this thing, this is this, right? Softmax ka prediction. And if you do model VGG dot layers, and if you do -1 and then you do output, this will be also the same, right? So rather than doing this, we could have set the model at model VGG dot layers, and then we could have set -2 dot output. So what it would have taken, it could have taken the answers from the FC2 layer, right? Where it has the ReLU activation function. You can see here FC2 with ReLU activation, whereas the last layer has prediction softmax. Let me show you this thing so that you don't have doubts. But just replace this. But what I have to do is I have to rerun the whole thing now. Restart the kernel and then rerun everything. Very easy. It won't take much time, right? This you have run this also, then you have to run this, then this. So right now, see, right now you are getting in the final summary, you were getting a prediction layer also, but now you won't see, right? See, you have only FC, then FC1 dense, FT2 dense, and then you have dense 1 and dense 2, right? You could have add more layer here. Let's say if I would have been at your place, I would have not dropped it directly to this. I could have simply done this 1000 also. It depends how are you dropping your model. Now what I've done is I've add one more layer. So FC1, FC2, 4096, then I've dropped to 1024, then dropping to 512 and then 2. You have 124 million trainable parameters that will train through this thing. Imagine the complexity the model is going to have. This was one error that we had to remove, but we have removed, and then we have got this thing out there, right? That's it.
Just a quick info, guys. Intellipaat provides artificial intelligence online training mentored by industry experts. The course link of which is given in the description below. So guys, we have come to the end of the session. If you have any doubts, please put down in the comment section below. We will try to answer it as soon as possible. Hope you all enjoyed the session. Thanks for watching.